Subscribe to the channel so you don't miss out on any of these videos. Imagine something so powerful that it defies the very laws of physics we've spent centuries trying to understand. Something so strange that even the greatest minds in science struggle to explain it. Now, picture that this something isn't just theoretical. It's out there, lurking in the cosmos, hidden within the hearts of black holes. These are spacetime singularities, the most mysterious objects in the universe, where our understanding of reality itself starts to crumble. At the center of every black hole lies a singularity, a place where gravity becomes infinite, and the fabric of space and time twists beyond recognition. But here's the catch: we don't fully know what's actually going on in a singularity. The math breaks down. The rules we rely on, like Einstein's theory of general relativity, stop working. This isn't just a mystery. It's a paradox that threatens to rewrite everything we think we know about the universe. What exactly is a singularity? Why do black holes even have them? And what does their existence tell us about the nature of reality itself? These aren't just questions for scientists. They're questions that touch the very edge of human curiosity. By the end of this video, you'll not only understand why singularities are so baffling, but you'll also see how they force us to confront one of the greatest unknowns of all: the limits of human knowledge. Let's start by breaking this down. A singularity is, in theory, a point in space where the density of matter becomes infinite. That sounds impossible, right? After all, how can anything have infinite density? To put it simply, imagine taking an entire star, something millions of times the mass of our Sun, and crushing it down into a single point. That's what happens at the center of a black hole. The force of gravity becomes so intense that it overrides every other force in the universe, pulling everything into this one point where the rules of physics collapse. Here's the problem: infinite density isn't something we can really measure or observe. It's a concept that pops out of our equations, but we have no way to test it. And that's where things get tricky. You see, physics is based on models and theories that explain how things work. But when we encounter a singularity, the math becomes inconsistent. It's like trying to divide by zero. It just doesn't compute. This raises a huge question. If our current understanding of physics can't describe singularities, does that mean our theories are wrong? Or is there a deeper layer of reality we haven't uncovered yet? To answer this, we need to dive deeper into the two pillars of modern physics: general relativity and quantum mechanics. General relativity, proposed by Albert Einstein over a century ago, describes how gravity works on a large scale. It's incredibly successful at explaining everything from the orbits of planets to the bending of light by massive objects. But when it comes to singularities, general relativity falls apart. The equations give us nonsensical results, like infinite curvature of space-time and zero volume. On the other hand, quantum mechanics governs the world of the very small, atoms, particles, and the fundamental building blocks of matter. Unlike general relativity, quantum mechanics doesn't deal well with gravity. So when you try to combine these two frameworks to describe what happens inside a singularity, you run into a wall. This conflict between general relativity and quantum mechanics is one of the biggest problems in physics today. Scientists are searching for a unified theory, often called quantum gravity, that could bridge the gap between these two worlds. Some theories, like string theory and loop quantum gravity, offer potential solutions. But none have been fully proven. One of the most intriguing ideas comes from Stephen Hawking, who proposed that black holes might not actually trap everything forever. According to Hawking, black holes slowly emit radiation, a phenomenon now known as Hawking radiation. Over incredibly long periods of time, this radiation causes the black hole to lose mass and eventually disappear. But here's the twist: if a black hole evaporates, what happens to the singularity inside it? Hawking's idea leads to another mystery: the information paradox. In quantum mechanics, information about particles, like their position and state, can't be destroyed. But if a black hole evaporates and its singularity vanishes, does the information about everything that fell into it disappear too? This question has puzzled scientists for decades and remains unresolved. Another angle to consider is how singularities challenge our concept of time. Inside a black hole, time doesn't flow in the way we experience it. In fact, as you approach the singularity, time slows down relative to the outside universe. At the singularity itself, time might stop altogether, or it might not even exist in the way we understand it. These mind-bending possibilities aren't just theoretical, they have profound implications for understanding the universe. Singularities force us to rethink concepts like cause and effect, the nature of reality, and even the origin of the universe itself. Some scientists speculate that the Big Bang, the event that created our universe, might have been a type of singularity. But here's where things get even stranger. Recent studies suggest that singularities might not be points at all. Instead, they could be regions of extremely warped spacetime with finite size. This idea challenges the traditional view of singularities as infinitely small points and opens up new possibilities for understanding them. And yet, despite all these theories, we've never directly observed a singularity. Black holes, by their very nature, are hidden from view. Their intense gravity prevents light from escaping, which means we can't see what's inside. Instead, we study black holes indirectly, by observing their effects on nearby stars, gas, and light. Even with groundbreaking achievements like the Event Horizon Telescope capturing the first image of a black hole's shadow, the singularity itself remains hidden. It's like looking at the edges of a secret, knowing there's something incredible in the center but being unable to reach it. This leads us to the big question: will we ever truly understand singularities? Some physicists believe we'll need entirely new laws of physics to explain them. Others think singularities might not exist in the way we imagine. They could be artifacts of our incomplete understanding of gravity. One possibility is that singularities are simply placeholders in our equations, pointing us toward a deeper truth. If we can develop a theory of quantum gravity, we might discover that singularities aren't infinite at all, that they're governed by rules we just don't know yet. If singularities aren't infinite, what could they actually be? One hypothesis is that they might represent the densest possible configuration of matter allowed by the laws of physics. In this scenario, instead of being a point of infinite density, a singularity could be a region of spacetime where matter is compressed to a finite but unimaginably high density. This idea aligns with some interpretations of loop quantum gravity, a theory that attempts to merge quantum mechanics and general relativity. Loop quantum gravity suggests that spacetime itself isn't smooth but is instead made up of tiny, discrete loops. At the scale of a singularity, these loops could resist further compression, preventing the formation of infinite density. Instead of collapsing into a single point, the matter might settle into an extremely compact but finite structure. If this is true, it would mean that singularities don't break the laws of physics, they just push them to their limits. Another fascinating possibility is that singularities might act as portals to other regions of spacetime. This idea stems from solutions to Einstein's equations that describe hypothetical structures called wormholes. Wormholes are shortcuts through spacetime, connecting distant points in the universe or even different universes altogether. Some scientists speculate that the singularity at the center of a black hole could be connected to another singularity, creating a wormhole. If this is the case, then black holes might not be the ultimate dead ends we think they are. Instead, they could be gateways to other parts of the universe, or perhaps even to entirely new universes. However, there's a catch. Wormholes, if they exist, are thought to be incredibly unstable. Any matter entering the wormhole would likely cause it to collapse almost instantly, making it impossible to travel through. Still, the idea of singularities as cosmic doorways is tantalizing. It raises the question of whether our universe itself might have been born from a singularity. According to the Big Bang theory, the universe began as a singularity roughly 13.8 billion years ago. This singularity wasn't a black hole but rather a point where all the matter, energy, and spacetime of the universe were compressed into an incredibly hot, dense state. The Big Bang singularity is different from the singularities inside black holes in several ways. For one, it represents a beginning rather than an endpoint. Instead of collapsing inward, the Big Bang's singularity expanded outward, creating space and time as it went. But the similarities between the two are striking enough that some scientists wonder if they're connected. One speculative idea is that black hole singularities might give birth to new universes. When matter collapses into a black hole, it could reach the singularity and then bounce into a new realm of spacetime, creating a new universe on the other side. If this is true, then our universe might be the offspring of a black hole in another universe. And the black holes in our universe might be creating new universes of their own. This concept is part of a broader idea known as the multiverse, which suggests that our universe is just one of many. Within this framework, singularities play a crucial role as cosmic seeds, each one spawning a new universe with its own unique properties and physical laws. Of course, these ideas are highly speculative. We have no direct evidence for the multiverse or for singularities acting as portals to other universes. But they highlight just how much we don't know about singularities and their place in the cosmos. Singularities also force us to confront philosophical questions about the nature of reality. For example, if singularities represent places where the laws of physics break down, does that mean the universe is fundamentally unknowable? Or are singularities simply a sign that our current theories are incomplete? These questions challenge the very foundation of science, which is built on the idea that the universe is governed by consistent, discoverable laws. If singularities exist outside those laws, they might represent a boundary to human understanding, a place where our tools of observation and reasoning can't reach. But there's also a more optimistic view. Singularities could be the key to unlocking a deeper understanding of the universe. By studying them, we might discover new principles of physics that reveal hidden layers of reality. This has already happened in the past. Einstein's theory of general relativity, for example, emerged from questions about the nature of gravity and motion. Similarly, the quest to understand singularities could lead to breakthroughs that revolutionize our understanding of the cosmos. One of the most exciting areas of research in this field is the study of black hole interiors. While we can't observe what's inside a black hole directly, scientists are using computer simulations and mathematical models to explore what might be happening near the singularity. These studies suggest that the interior of a black hole could be far more complex than we imagined. Some models propose that black holes might contain quantum foam, a chaotic, ever-changing structure of spacetime at the smallest scales. Others suggest that singularities might be surrounded by a region of spacetime where quantum effects dominate, creating a sort of quantum shield that prevents the formation of true singularities. Then there's the idea of cosmic censorship. This hypothesis, first proposed by physicist Roger Penrose, suggests that singularities are always hidden from view by the event horizon of a black hole. According to this idea, nature has a built-in mechanism to protect us from directly observing singularities. But not all scientists agree. Some believe that naked singularities, singularities without an event horizon, could exist in certain conditions. If naked singularities are real, they would be unlike anything else in the universe. They would expose the raw, unfiltered nature of spacetime in its most extreme form, offering a direct window into the breakdown of physics. But they would also be incredibly dangerous. The intense gravitational forces near a naked singularity could distort spacetime so severely that it would disrupt the structure of the universe itself. As we continue to explore these mysteries, one thing becomes clear: singularities are not just a problem for physicists. They are a profound reminder of how much we still have to learn about the universe. They challenge us to think beyond the limits of our current understanding and to embrace the unknown with curiosity and determination. If naked singularities exist, their implications extend far beyond theoretical physics. They would not only reshape our understanding of spacetime but also test the very limits of what can be known about the cosmos. One of the reasons this idea is so controversial is that it challenges the principle of determinism, the idea that the present state of the universe determines its future. Near a naked singularity, the extreme warping of spacetime could render the future unpredictable, breaking down the very foundation of cause and effect. To grasp the scale of such implications, consider the concept of gravitational lensing, which occurs when a massive object, like a black hole, bends light around it due to its immense gravity. Near a naked singularity, the gravitational effects would be so extreme that light could potentially loop infinitely or scatter unpredictably. This would create visual phenomena unlike anything seen in the cosmos: distortions, echoes of light, and even images of distant objects duplicated and warped in ways that defy logic. The existence of naked singularities would also force us to rethink the boundaries of space and time. Within general relativity, singularities are places where spacetime becomes infinitely curved. But if these regions are exposed, they could reveal new dimensions or structures of spacetime that we've never even theorized. Some researchers speculate that naked singularities might act as windows into other universes, offering a direct connection between our reality and entirely separate realms of existence. Yet, despite the allure of these ideas, the existence of naked singularities is far from confirmed. The cosmic censorship hypothesis, while unproven, has been a cornerstone of black hole physics for decades. It acts as a safeguard, suggesting that the universe has a sort of natural order that prevents such anomalies from disrupting the observable cosmos. But if cosmic censorship fails, it would mean that the universe is far stranger, and far less orderly, than we ever imagined. This brings us to another profound question: are singularities truly singular? Or do they represent something we haven't yet understood? Some researchers argue that what we call a singularity might not exist in the strictest sense. Instead, it could be an artifact of our incomplete theories. General relativity predicts singularities, but it doesn't account for quantum mechanics, which governs the behavior of matter and energy at the smallest scales. When quantum effects are included, some physicists believe that singularities might resolve into something entirely different, a structure or phenomenon that can be described by a future theory of quantum gravity. One such idea comes from string theory, which posits that the fundamental building blocks of the universe are not particles but tiny, vibrating strings of energy. According to some interpretations, these strings could prevent the formation of singularities by spreading out the energy and mass that would otherwise collapse into an infinitely small point. If string theory is correct, then the centers of black holes might not be singularities at all but rather fuzzballs of densely packed strings. This concept radically shifts our understanding of black holes and their singularities. Instead of being points where physics breaks down, fuzzballs would be objects that obey new, undiscovered laws of physics. Studying them could reveal deeper truths about the nature of matter, energy, and spacetime. Another approach to resolving singularities comes from loop quantum gravity. Unlike string theory, which introduces additional dimensions and entities, loop quantum gravity focuses on quantizing spacetime itself. This theory suggests that spacetime is not a smooth continuum but rather consists of tiny, discrete loops. At the scale of a singularity, these loops could resist further compression, creating a finite structure rather than an infinite point. This would eliminate the paradoxes associated with singularities while preserving the core principles of general relativity and quantum mechanics. These theories are still in their infancy, and much work remains to be done. But they offer a glimmer of hope that singularities are not the ultimate roadblock in our quest to understand the universe. Instead, they could be the key to a new era of physics, one that unites the macroscopic and microscopic, the cosmic and the quantum. Another fascinating avenue of exploration involves the potential connection between singularities and the early universe. The Big Bang, as mentioned earlier, is thought to have begun as a singularity. If this is true, then understanding the singularities in black holes could offer clues about the origins of the cosmos. Some scientists propose that the conditions near a singularity might mirror those that existed at the moment of the Big Bang. If we can decipher what happens in these extreme environments, we might unlock the secrets of creation itself. One particularly bold idea is that the universe might be cyclical, with singularities playing a crucial role in its ongoing evolution. In this scenario, black holes could act as cosmic recycling centers, compressing matter and energy into singularities that eventually bounce back, creating new universes. This idea aligns with some interpretations of quantum gravity, which suggests that spacetime can undergo dramatic transformations without breaking the fundamental laws of physics. Such theories are speculative, but they highlight the profound interconnectedness of singularities, black holes, and the broader universe. They remind us that singularities are not isolated anomalies but integral parts of the cosmic tapestry. By studying them, We are not just probing the limits of physics, we are exploring the very nature of existence. The quest to understand singularities also has practical implications. Black holes, for example, are not just theoretical constructs, they are real objects with measurable effects on their surroundings. Observing the behavior of matter and energy near black holes provides valuable data that can help refine our theories. Projects like the Event Horizon Telescope, which captured the first image of a black hole's event horizon, are paving the way for even more detailed studies of these enigmatic objects. As technology advances, we may one day be able to observe the interiors of black holes indirectly, using sophisticated simulations and instruments. These observations could reveal whether singularities are truly infinite, or if they represent something entirely different. They could also shed light on the mysterious relationship between black holes and the fabric of spacetime. One of the most exciting possibilities is that studying singularities could lead to new technologies. The extreme conditions near a singularity involve energies and forces far beyond anything we can currently produce on Earth. By understanding these conditions, we might discover new principles of energy generation, propulsion, or even communication. In this sense, singularities are not just a scientific puzzle, they are a potential gateway to the future. The technological implications of understanding singularities are profound. For instance, imagine harnessing the immense energy dynamics observed near black holes. The theoretical Penrose process suggests that it might be possible to extract energy from the rotation of a black hole. If we could fully understand and replicate the physics of such processes, humanity might one day develop methods for generating nearly limitless power. This might sound like science fiction, but it underscores how singularities, and the regions surrounding them, could become laboratories for groundbreaking technological advancements. Another potential application relates to spacetime manipulation. Singularities are regions where spacetime is so drastically warped that time itself behaves in ways unimaginable in our everyday experience. If we could harness even a fraction of the spacetime warping phenomena associated with singularities, it might lead to technologies that could revolutionize transportation or even communication. For example, theoretical constructs like wormholes, which might connect distant regions of spacetime, could rely on the extreme conditions near singularities. Such advancements could make interstellar travel a reality, reducing journeys that would take millennia to mere seconds. This brings us to another tantalizing aspect of singularities: their potential role in solving the mysteries of time itself. Singularities are a nexus where time, as we understand it, ceases to function normally. Near a black hole, time dilates, slowing down relative to an observer farther away. As you approach the event horizon, time appears to stretch infinitely. But what happens beyond that? If singularities could be studied or modeled in greater detail, they might reveal the true nature of time, including whether it has a beginning, an end, or exists in ways we have yet to comprehend. The implications for time travel, while speculative, are deeply tied to the study of singularities. Some physicists propose that the intense warping of spacetime near singularities might allow for closed time-like curves, paths through spacetime that loop back on themselves. If such paths exist and can be navigated, they could theoretically enable time travel. While this remains firmly in the realm of theory, it demonstrates how singularities could fundamentally alter our understanding of temporal mechanics. However, exploring singularities isn't without its challenges. The very nature of these entities makes direct observation impossible with current technology. The intense gravity of a black hole means that no information can escape once it crosses the event horizon. This is why much of what we know about singularities comes from mathematical models and indirect observations. Advanced simulations, like those using quantum computers, might one day provide a clearer picture. But for now, singularities remain shrouded in mystery, an enigma that tests the limits of human ingenuity. Yet, the quest to understand singularities isn't just about solving equations or creating simulations. It's also a deeply philosophical endeavor. Singularities force us to confront questions about the nature of reality itself. What does it mean for spacetime to break down? Is the universe governed by unchanging laws, or are there exceptions hidden in its deepest corners? Can the human mind ever truly grasp the infinite? These are not just scientific questions, they are existential ones, touching on the very essence of what it means to be a curious, sentient being. Furthermore, singularities challenge our intuitive understanding of scale. The idea of something being infinitely small and infinitely dense defies our everyday experiences. It forces us to think beyond the constraints of the physical world we inhabit. In this sense, studying singularities is as much an exercise in expanding the boundaries of imagination as it is in advancing science. The study of singularities also has implications for the search for extraterrestrial intelligence. If advanced civilizations exist elsewhere in the universe, it's plausible that they have already encountered or even studied singularities. Their understanding of these phenomena could far surpass our own, potentially leading to technologies or insights that we can only dream of. If we ever make contact with such civilizations, their knowledge of singularities might be one of the most valuable things they could share. Another area of intrigue is the relationship between singularities and information. The information paradox arises because the laws of quantum mechanics suggest that information cannot be destroyed, while general relativity implies that anything falling into a singularity is effectively lost to the universe. This paradox has sparked intense debate among physicists, with some proposing that information might be stored on the event horizon of a black hole in the form of quantum holograms. If this is true, it would not only resolve the paradox but also revolutionize our understanding of information storage and retrieval at the most fundamental level. The concept of singularities also extends beyond black holes. The Big Bang itself is often described as a singularity, a point where the density of the universe was infinite, and the laws of physics as we know them broke down. This raises profound questions about the nature of the cosmos. Is our universe the result of a singularity? And if so, what caused it? Was it a unique event, or are there countless other universes born from their own singularities? These questions sit at the intersection of physics, cosmology, and philosophy, reminding us that singularities are not just theoretical constructs but pivotal elements in the story of existence. Some researchers even speculate about white holes, the hypothetical opposites of black holes. While black holes draw matter and energy in, white holes would expel it. If white holes exist, they might be connected to black holes through wormholes, forming a sort of cosmic loop. This idea, while speculative, suggests that singularities could be part of a larger, interconnected system that governs the flow of matter, energy, and information across the universe. Ultimately, singularities represent both the greatest challenge and the greatest opportunity in modern physics. They are the ultimate unknown, the point where our current theories falter and our imagination takes over. But they are also a source of hope, a reminder that the universe is far more complex, mysterious, and wondrous than we can yet comprehend. Each step we take toward understanding singularities brings us closer to unraveling the deepest secrets of the cosmos, opening new doors to discovery, innovation, and enlightenment. The idea of white holes, while largely theoretical, adds another layer of complexity to our understanding of singularities and spacetime. Unlike black holes, which trap everything within their event horizons, white holes theoretically do the opposite. They eject matter and energy, allowing nothing to enter. This concept, first suggested as a solution to Einstein's field equations, implies that black holes and white holes could be interconnected through a bridge of spacetime, often referred to as a wormhole. Such a connection could create a dynamic system where matter and energy flow from one end, the black hole, to the other, the white hole. If white holes exist, they would challenge our current understanding of entropy and the flow of time. In classical physics, entropy always increases, meaning systems move from order to disorder. A white hole, expelling matter and energy, would appear to reduce entropy locally, contradicting this fundamental principle. This potential reversal of entropy would not only shake the foundations of physics but also lead to revolutionary insights into the nature of time and causality. Wormholes, often referred to as Einstein-Rosen bridges, could play a crucial role in connecting singularities. If black holes and white holes are endpoints of such a bridge, they might serve as a shortcut through spacetime. While the mathematics of wormholes is elegant, their practicality remains deeply uncertain. To stabilize a wormhole, Exotic matter with negative energy density would likely be required, a concept that has yet to be proven possible. Nonetheless, the prospect of wormholes as conduits for faster-than-light travel continues to inspire scientists and storytellers alike. One fascinating implication of wormholes is their potential use as time machines. If one end of a wormhole experiences time dilation relative to the other, it might allow for time travel, at least theoretically. This idea has led to debates about causality and the possibility of paradoxes, such as the famous grandfather paradox, where altering the past could change the future in unpredictable ways. Singularities, as the anchors of such phenomena, would be central to any exploration of these mind-bending concepts. Returning to the role of singularities in black holes, it's worth exploring the nature of the event horizon. This boundary is not just a point of no return for matter and light, but also a region where spacetime becomes infinitely warped. The event horizon acts as a cosmic veil, hiding the singularity from external observers. However, advances in technology, such as gravitational wave detectors and high-resolution telescopes, are allowing us to study these horizons more closely, shedding light on the behavior of matter and energy in these extreme environments. The discovery of gravitational waves, ripples in spacetime caused by massive accelerating objects, has been a game-changer in our understanding of singularities. When two black holes merge, they produce powerful gravitational waves that carry information about their masses, spins, and other properties. By analyzing these waves, scientists can indirectly study the singularities at the heart of these black holes. This indirect observation provides invaluable data, helping to refine our models and theories. One of the most intriguing aspects of black hole mergers is the phenomenon of ring down. After two black holes merge, the resulting black hole undergoes oscillations, emitting gravitational waves in a process akin to a bell ringing after being struck. These ring down signals provide a unique opportunity to test the properties of singularities and the surrounding spacetime. If deviations from expected behavior are observed, they could indicate new physics beyond general relativity. The study of singularities also intersects with the search for a unified theory of physics. General relativity, which describes gravity, and quantum mechanics, which governs the behavior of particles at the smallest scales, are fundamentally incompatible at singularities. This disconnect suggests that our understanding of the universe is incomplete. Singularities may hold the key to reconciling these two pillars of modern science, potentially leading to a theory of everything. String theory, one of the leading candidates for a unified theory, offers intriguing possibilities for understanding singularities. In string theory, particles are not point-like but rather tiny vibrating strings. This framework eliminates the infinite densities predicted by classical physics, replacing them with finite, calculable quantities. If string theory is correct, it could revolutionize our understanding of singularities, transforming them from mathematical abstractions into tangible, physical phenomena. Another theoretical approach is loop quantum gravity, which posits that spacetime itself has a discrete, granular structure. In this model, singularities might not be infinitely dense but rather regions where spacetime is quantized. This concept challenges traditional views of singularities, offering a new lens through which to study the origins and fate of the universe. The implications of singularities extend to the multiverse hypothesis, which suggests that our universe is just one of many. If singularities exist at the centers of black holes, they could serve as gateways to other universes. In this scenario, black holes might not just be cosmic dead ends but rather portals to entirely new realms of existence. This idea, while speculative, aligns with some interpretations of quantum mechanics and the theory of cosmic inflation. As we delve deeper into the mysteries of singularities, one thing becomes clear: they are not just anomalies to be explained away but fundamental components of the universe. They challenge our assumptions, push the boundaries of our knowledge, and inspire us to ask the most profound questions about existence. Singularities are a testament to the boundless complexity of the cosmos, reminding us that the more we learn, the more there is to discover. The quest to understand singularities is far from over. With each new discovery, we move closer to unraveling their secrets. From the quantum realm to the vast expanse of spacetime, singularities are a beacon of mystery, drawing us ever closer to the ultimate truths of the universe. The idea of singularities as gateways to other universes may sound like science fiction, but it stems from serious theoretical considerations. The concept ties into the broader multiverse hypothesis, where our universe is just one in an ensemble of countless others. This hypothesis arises naturally in certain cosmological models, particularly those based on the idea of eternal inflation. In this framework, inflationary bubbles might spawn their own universes, each with unique physical laws and constants. Singularities, such as those within black holes, could play a role in this cosmic tapestry by creating conditions suitable for the birth of new universes. If this is true, the implications are staggering. Each black hole in our universe could represent the seed of a new universe, with its own spacetime emerging from the singularity. This idea is speculative, but it resonates with certain interpretations of quantum mechanics, where probabilities govern events, and alternate outcomes might correspond to alternate realities. It also aligns with the holographic principle, which suggests that the information inside a black hole could encode the physics of an entirely different cosmos. The holographic principle itself is another fascinating tangent when discussing singularities. It posits that all the information contained within a volume of space can be represented on a lower dimensional boundary, much like a hologram. For black holes, this boundary is the event horizon. The principal challenges our traditional understanding of dimensionality and locality, hinting at deeper layers of reality that remain hidden from us. Could singularities, as repositories of immense information, hold the blueprints for the structure of the universe? And if so, how can we decode them? Theoretical physicists are actively pursuing these questions, often using black holes as natural laboratories. One intriguing area of research is the connection between black hole thermodynamics and quantum information theory. Black holes are not entirely black. They emit radiation, a phenomenon first described by Stephen Hawking. This Hawking radiation arises due to quantum effects near the event horizon, where particle-antiparticle pairs form. Over time, this radiation leads to the gradual evaporation of the black hole, raising profound questions about the fate of the information contained within. The so-called black hole information paradox lies at the heart of this discussion. If a black hole evaporates completely, does the information about everything it once contained vanish as well? This idea contradicts the principle of quantum mechanics, which asserts that information cannot be destroyed. Resolving this paradox could require a radical rethinking of our understanding of spacetime and quantum theory, potentially leading to breakthroughs that illuminate the true nature of singularities. One of the leading ideas to address the information paradox is the notion of black hole complementarity. This principle suggests that the information encoded on the event horizon and the information falling into the black hole are two complementary descriptions of the same phenomenon. To an external observer, all the information about matter entering the black hole is smeared across the event horizon. Meanwhile, for an observer falling into the black hole, that information continues to exist inside, albeit inaccessible from the outside. While this theory preserves the integrity of quantum mechanics, it remains controversial and continues to be tested against new findings. Another contender is the concept of firewalls. This hypothesis suggests that the event horizon of a black hole might be surrounded by a highly energetic zone that incinerates anything trying to pass through. Firewalls would fundamentally alter our understanding of black holes and their singularities, as they would effectively block information from ever entering. However, this idea is at odds with the predictions of general relativity, creating a tension that has yet to be resolved. These debates highlight the deep uncertainty surrounding the nature of singularities. As our understanding evolves, new tools and technologies are helping to bridge the gaps. Advanced telescopes like the Event Horizon Telescope, EHT, allow scientists to directly image black holes, offering unprecedented insights into their properties. The groundbreaking image of the supermassive black hole at the center of the galaxy M87, captured in 2019, marked a historic milestone. By studying the light emitted from the material orbiting the event horizon, researchers can probe the extreme physics near the singularity. Gravitational wave observatories like LIGO and Virgo are also shedding light on black holes and their singularities. These facilities detect the ripples in spacetime produced by cataclysmic events like black hole mergers. Each detection provides a treasure trove of data, offering clues about the masses, spins, and dynamics of the merging black holes. The more we observe, the more we learn about how singularities interact with their environments. As we continue to push the boundaries of observation and theory, one thing becomes increasingly clear: singularities are not merely theoretical curiosities. They are the engines of cosmic evolution, shaping galaxies, powering quasars, and perhaps even influencing the birth and fate of universes. Yet they remain shrouded in mystery, defying our attempts to fully comprehend them. Singularities force us to confront the limits of human knowledge and imagination. They sit at the intersection of the known and the unknown, challenging us to rethink our assumptions about reality. In doing so, they serve as a powerful reminder of the complexity and wonder of the universe, a cosmos that, despite our best efforts, still holds many secrets. Our journey to understand singularities is far from over. Each step brings new questions and new opportunities for discovery. From black holes to white holes, from wormholes to the multiverse, the study of singularities invites us to explore the most profound aspects of existence. And while we may never fully unravel their mysteries, the quest itself is a testament to the unyielding human spirit and our insatiable curiosity about the universe we call home. The mysteries surrounding singularities don't just challenge our understanding of physics, they push us to consider the very fabric of reality and our place within it. Singularities represent regions where our current theories break down, suggesting that our grasp of the universe is incomplete. They reveal the need for a unifying theory that can reconcile the principles of general relativity, which governs the cosmos on large scales, with quantum mechanics, which dominates the subatomic world. One of the most pressing questions is, what happens inside a black hole? The singularity at its core is described as a point of infinite density, where the curvature of spacetime becomes infinite. This description comes directly from Einstein's equations, yet it's widely acknowledged that infinities in physics are red flags, signs that the theory is being stretched beyond its limits. A deeper, more fundamental framework is needed to understand what truly lies within these enigmatic regions. The idea that singularities might not actually exist as points of infinite density but instead represent a breakdown in our mathematical models is an appealing one. In this view, singularities are not physical objects but rather placeholders for our ignorance. This perspective has led researchers to seek alternative descriptions of black holes that avoid infinities. Loop quantum gravity, for example, suggests that spacetime is quantized, composed of discrete units, much like matter is composed of atoms. In this framework, singularities might be replaced by quantum bridges, or bounces, that connect to other regions of spacetime. Another approach involves string theory, which posits that the fundamental building blocks of the universe are not point-like particles but one-dimensional strings. In string theory, the concept of a singularity might be smoothed out, with strings replacing the infinitely dense point at the heart of a black hole. These strings could vibrate in ways that encode information about the black hole's properties, providing a new way to understand its structure. The implications of these theories extend far beyond black holes. They suggest that singularities might have played a crucial role in the birth of our universe. The Big Bang, often thought of as a singularity, marked the beginning of time and space as we know them. But if singularities are smoothed out or replaced by other structures in quantum gravity, the Big Bang might not have been a true beginning. Instead, it could represent a transition from a previous state of the universe, possibly a bounce, from a collapsing cosmos to an expanding one. This idea, often called the Big Bounce theory, challenges the traditional notion of a singular beginning to the universe. It suggests that time and space could be cyclical, with periods of expansion followed by contraction. Singularities in this framework are not endpoints but rather turning points, connecting one phase of the universe to the next. If true, this would mean the universe has no ultimate beginning or end, fundamentally altering our understanding of time. The study of singularities also forces us to confront philosophical questions about the nature of reality. Are singularities physical entities, Or are they artifacts of our incomplete theories? Do they represent boundaries beyond which we cannot observe, or are they gateways to new realms of existence? These questions lie at the intersection of physics and philosophy, revealing the deep interplay between science and our quest to understand the universe. One of the most profound aspects of singularities is their ability to inspire awe and wonder. They remind us that the universe is far more complex and mysterious than we can currently comprehend. Yet they also serve as a testament to human ingenuity. Our ability to theorize about such extreme phenomena, even in the absence of direct observation, demonstrates the power of the human mind to explore the unknown. As we continue to study singularities, we are not just seeking answers about black holes or the origins of the universe. We are also exploring the boundaries of human knowledge, pushing the limits of what we can understand. Each discovery brings us closer to a deeper understanding of the cosmos and our place within it. And while singularities may remain elusive, their mysteries will continue to inspire generations of scientists, philosophers, and dreamers. The journey to unravel the secrets of singularities is far from over. With each passing year, new technologies and theoretical advancements bring us closer to understanding these enigmatic regions. Whether they are cosmic dead ends, gateways to other universes, or something entirely different, singularities hold the key to some of the most profound questions in science. And in seeking to answer those questions, we are not just exploring the universe, we are exploring the very nature of existence itself. Our exploration of singularities takes us to the heart of physics' greatest challenge, unifying general relativity and quantum mechanics into a single framework often called quantum gravity. Singularities are the battleground where these two pillars of modern physics clash. General relativity predicts their existence, but quantum mechanics suggests that infinities like those at singularities cannot exist in a complete theory. Resolving this conflict would not only clarify the nature of singularities but also unlock new insights into the fundamental workings of the universe. One of the most intriguing concepts emerging from efforts to understand singularities is the holographic principle. Originally proposed in the context of black holes, it posits that all the information within a volume of space can be represented on its boundary surface. For a black hole, this boundary is the event horizon, where information about everything that falls into the black hole might be encoded. This principle challenges our conventional understanding of dimensionality, suggesting that the three-dimensional world we experience might be a projection of two-dimensional information. The holographic principle has far-reaching implications. It suggests that spacetime itself might emerge from more fundamental structures, possibly described by quantum entanglement. Entanglement, a phenomenon where particles become interconnected such that the state of one instantly influences the state of another, even across vast distances, is a cornerstone of quantum mechanics. Recent research has hinted that the fabric of spacetime could be woven from a network of entangled quantum states. In this view, singularities could represent points where this entangled network breaks down or transforms into something entirely different. These ideas are not purely theoretical. They have practical implications for understanding the universe's most extreme environments, such as the interiors of black holes and the conditions immediately after the Big Bang. In these regimes, where gravity is incredibly strong and quantum effects dominate, the holographic principle and related concepts offer a potential roadmap for bridging the gap between general relativity and quantum mechanics. The study of singularities also intersects with cosmology, particularly in understanding the universe's early moments. The Big Bang is often described as a singularity, a point of infinite density and temperature where the known laws of physics break down. However, if singularities are artifacts of our incomplete theories, the Big Bang might not have been a true singularity. Instead, it could represent a transition from a prior state of the universe, as suggested by the Big Bounce theory and other models. These alternative models challenge the traditional view of the universe's origin. They propose that the universe might have undergone cycles of expansion and contraction or emerged from a pre-existing state of quantum fluctuation. In these scenarios, singularities are not endpoints but moments of transformation, where one phase of cosmic evolution gives way to another. These ideas are speculative but grounded in efforts to reconcile observations of the universe's large-scale structure with the principles of quantum mechanics and general relativity. Theoretical developments are also shedding light on the nature of black hole singularities. For example, some models suggest that the singularity at a black hole's center could be replaced by a quantum core, sometimes called a Planck star. In this view, the immense density of the collapsing matter is counteracted by quantum effects, preventing the formation of an infinite singularity. Instead, the black hole's core becomes a region of incredibly dense but finite matter, governed by the laws of quantum gravity. This idea not only avoids the infinities predicted by classical relativity, but also offers a potential solution to the black hole information paradox. The concept of Planck stars connects to broader questions about the fate of information in black holes. If black holes eventually evaporate through Hawking radiation, what happens to the information they contain? Theories like the holographic principle and Planck stars suggest that this information is not lost but encoded in subtle ways, potentially on the event horizon or within the quantum structure of spacetime itself. Resolving this paradox could revolutionize our understanding of both black holes and the universe. Singularities also raise fascinating questions about causality and time. Inside a black hole, the structure of spacetime becomes so distorted that the normal flow of time breaks down. In theory, this could create regions where time loops back on itself or where cause and effect become ambiguous. These possibilities challenge our everyday understanding of time and suggest that singularities could hold the key to unraveling its true nature. The notion of time loops and causal ambiguity connects to the idea of wormholes, hypothetical tunnels through spacetime that could connect distant regions or even different universes. Some theories suggest that singularities might serve as entry or exit points for wormholes, making them potential gateways to other dimensions. While purely speculative at this stage, these ideas capture the imagination and drive efforts to understand the exotic possibilities inherent in the physics of singularities. As our understanding of singularities deepens, we are likely to uncover even more surprising connections between seemingly unrelated areas of physics. For example, the study of black holes and singularities has already inspired advances in quantum computing, where concepts like entanglement and information storage are critical. It has also influenced our understanding of the early universe, where similar conditions of extreme density and energy prevailed. The journey to understand singularities is not just a scientific endeavor, it is a philosophical and existential quest. Singularities represent the limits of human knowledge, the points where our theories and intuitions falter. They remind us that the universe is far stranger and more complex than we can currently comprehend. Yet they also inspire us to push the boundaries of what is possible, to ask deeper questions, and to seek a more profound understanding of the cosmos. Singularities are more than just theoretical constructs or mathematical curiosities. They are windows into the unknown, inviting us to explore the most profound mysteries of existence. Whether they are cosmic endpoints, beginnings, or something entirely different, singularities challenge us to rethink our assumptions about the universe and our place within it. And in doing so, they remind us of the boundless potential of human curiosity and imagination. Singularities are not just a doorway to understanding the cosmos. They are a reminder of the universe's boundless creativity and chaos. They mark the points where the rules of physics as we know them dissolve into the unknown, leaving us with more questions than answers. But what if singularities are not anomalies? What if they are essential building blocks of the cosmic architecture? To explore this idea, we must dive deeper into how singularities challenge, and perhaps rewrite, our understanding of the cosmos. At the heart of every singularity lies a paradox. They are both the culmination of order and the birthplace of chaos. They represent the ultimate convergence of forces, where gravity becomes so intense that it warps spacetime beyond recognition. But rather than existing as isolated phenomena, singularities may be the cosmic threads that weave together the universe. They might not just be the cores of black holes, but could also be tied to the structure of the universe at its largest scales. One idea that has gained traction in theoretical physics is that singularities could act as cosmic seeds, playing a role in galaxy formation and evolution. When a massive star collapses into a black hole, the singularity that forms could exert such an intense gravitational pull that it draws in surrounding matter, forming the accretion disks and jets we observe in quasars. Over time, This process might shape entire galaxies, suggesting that singularities are not merely the end points of stellar evolution but are instrumental in cosmic growth. But the role of singularities might extend even further. Some researchers propose that singularities could be the birthplaces of entire universes. This idea stems from the concept of white holes, the theoretical opposites of black holes. While black holes pull matter and light inward, white holes are hypothesized to expel matter and energy outward. If white holes exist, they might be connected to black holes through wormholes, creating a cosmic recycling system where matter falls into one universe and emerges in another. This speculative idea leads to the concept of a multiverse, a collection of universes with varying physical laws, dimensions, and structures. If black hole singularities act as portals to other universes, our own universe could have emerged from the singularity of a black hole in a parent universe. This challenges the traditional view of the Big Bang as a singular event and instead frames it as a localized phenomenon within a much larger, interconnected multiverse. Even within our universe, singularities could be responsible for shaping spacetime in unexpected ways. The idea of cosmic censorship, proposed by physicist Roger Penrose, suggests that singularities are always hidden within event horizons, making them unobservable from the outside. However, recent research has questioned this principle, suggesting that naked singularities could exist without event horizons. If true, naked singularities could influence the surrounding universe in ways we have yet to understand, potentially revealing new insights into the nature of spacetime. The existence of naked singularities would also have profound implications for causality. In regions where the fabric of spacetime is infinitely warped, the distinction between past, present, and future might blur, creating loops or closed time-like curves. These phenomena could theoretically allow for time travel, though such ideas remain deeply speculative and fraught with paradoxes. Nonetheless, they highlight how singularities push the boundaries of not just physics but also our philosophical understanding of time and existence. Singularities may also hold the key to understanding dark energy, the mysterious force driving the accelerated expansion of the universe. Some theories suggest that dark energy could arise from the quantum effects of singularities scattered throughout spacetime. These singularities, though hidden within black holes or potentially existing at microscopic scales, might collectively influence the universe on a grand scale, acting as a kind of cosmic engine. This ties into the broader question of how singularities interact with the quantum realm. At scales smaller than atoms, quantum mechanics reigns supreme, describing a universe that is probabilistic rather than deterministic. Singularities challenge this framework because they represent a breakdown of spacetime itself, making it impossible to apply conventional quantum rules. Yet, some theories, like string theory and loop quantum gravity, aim to bridge this gap by describing singularities in terms of fundamental quantum structures. These approaches could reveal whether singularities are truly infinite or merely appear so because of our incomplete understanding. The potential quantum nature of singularities also raises the question of their stability. Are singularities eternal, or do they decay over time? If black holes emit Hawking radiation and gradually evaporate, what happens to the singularity at their core? Some theories suggest that as black holes shrink, their singularities might transform into entirely new entities, such as remnants or Planck stars, which could hold the answers to some of the deepest mysteries in physics. Ultimately, singularities are cosmic puzzles that challenge every aspect of our understanding. They force us to confront the limits of our knowledge and push us to develop new theories, tools, and ways of thinking. They remind us that the universe is not just a collection of stars and galaxies but a dynamic, ever-evolving system filled with phenomena that defy easy explanation. As we continue to explore singularities, we are not merely probing the extremes of physics. We are engaging with the deepest questions about the nature of reality, the origins of the cosmos, and our place within it. Singularities may represent the edges of our understanding, but they also inspire us to push beyond those edges, to venture into the unknown, and to seek a deeper connection with the universe. The deeper we venture into understanding singularities, the more we begin to appreciate their profound role in shaping our conception of the universe. These enigmatic points in spacetime, where gravity overwhelms everything else, do not just challenge existing physical theories but may ultimately redefine what we know about the very fabric of reality. Singularities are not isolated phenomena. They are deeply interconnected with the fundamental forces of nature and may even offer the key to unraveling the mysteries of the universe's birth, its expansion, and its eventual fate. A crucial aspect of singularities that demands attention is their relationship with the fundamental forces. At their cores, black holes and other singularities exhibit the effects of gravity at their most extreme. But gravity, as described by Einstein's general theory of relativity, is only one of four fundamental forces that govern the cosmos. The other three, electromagnetism, the strong nuclear force, and the weak nuclear force, operate on vastly different scales. These forces are governed by the laws of quantum mechanics, and herein lies the central issue. General relativity and quantum mechanics are incompatible when it comes to singularities. Quantum mechanics works wonders in the subatomic realm, describing particles, fields, and forces with remarkable precision. But when applied to singularities, quantum theory fails to provide a coherent description. This discrepancy suggests that our current understanding of physics is incomplete. To make sense of singularities, we need a theory that can merge general relativity with quantum mechanics, a theory of quantum gravity. In recent decades, several theoretical frameworks have emerged that attempt to bridge this gap. String theory, one of the most well-known candidates for a theory of quantum gravity, posits that the fundamental particles of the universe are not point-like objects but rather tiny, vibrating strings. These strings can exist in multiple dimensions, and their vibrations give rise to the forces and particles we observe. One of the remarkable features of string theory is that it naturally includes a quantum description of gravity, which could provide insights into the behavior of singularities. Loop quantum gravity is another approach, which focuses on quantizing spacetime itself. Unlike string theory, loop quantum gravity does not require the existence of extra dimensions. Instead, it treats spacetime as a network of discrete, finite loops, each representing the smallest possible unit of space. According to this theory, the Big Bang and the singularities inside black holes may not represent actual points of infinite density, but rather regions where the structure of spacetime itself becomes highly curved and quantum effects take over. Both string theory and loop quantum gravity are still works in progress, and no definitive conclusions have been reached about how they might explain singularities. Yet, they represent the most promising avenues for resolving one of the most profound challenges in modern physics. By incorporating quantum mechanics into our understanding of gravity, these theories could eventually shed light on what happens at the heart of singularities, perhaps revealing that they are not places of infinite destruction, but regions where new physical principles come into play. Another critical aspect of singularities that has sparked intense debate is their connection to the black hole information paradox. This paradox arises from the idea that information about the matter that falls into a black hole seems to be lost forever. According to the laws of quantum mechanics, however, information can never truly be destroyed. This creates a fundamental contradiction, as the singularity at the center of a black hole seems to erase all trace of the information that falls within it. Over the years, various proposals have been put forward to resolve this paradox. One of the most intriguing is the idea of black hole complementarity. This theory suggests that the information is not destroyed but rather encoded in a highly scrambled form on the event horizon of the black hole, beyond the point of no return. Some physicists propose that the information is preserved in a quantum mechanical sense, but in a way that is inaccessible to observers who are outside the black hole's event horizon. Another approach to resolving the black hole information paradox involves the firewall hypothesis, which posits that an energetic barrier exists just inside the event horizon, effectively destroying anything that falls into the black hole. This would mean that information is not lost, but rather that it is erased as soon as it crosses the horizon. While this idea has its critics, it highlights the lengths to which scientists are willing to go to reconcile quantum mechanics with general relativity. The holographic principle, mentioned earlier, offers another perspective on the information paradox. This idea, based on insights from string theory and black hole physics, suggests that all the information contained within a volume of space can be represented on its boundary. For a black hole, this boundary would be its event horizon. According to this principle, the information that falls into a black hole is not lost but rather encoded on the event horizon in a way that is compatible with quantum mechanics. The holographic principle is still a topic of active research, but it has the potential to resolve the black hole information paradox and provide new insights into the nature of singularities. As we consider these diverse ideas and hypotheses, we are reminded of the extraordinary complexity of the universe. Singularities, once thought to be mathematical curiosities or mere theoretical oddities, have emerged as central to our understanding of spacetime, gravity, and the fundamental laws of nature. They are the frontiers where our current theories of physics break down, but they are also the places where new theories will emerge. In the not-too-distant future, advancements in both theoretical physics and observational astronomy may provide the breakthroughs needed to unlock the mysteries of singularities. New techniques in gravitational wave astronomy, which allows scientists to detect ripples in spacetime caused by events like black hole mergers, may offer direct evidence of the extreme environments where singularities reside. Similarly, future space telescopes, such as the James Webb Space Telescope, may give us a clearer view of the regions surrounding black holes, offering indirect clues about what happens at their cores. Ultimately, the study of singularities is more than just an academic pursuit. It is a quest to understand the nature of reality itself, to push the limits of human knowledge, and to explore the deepest questions of existence. As we continue to probe these enigmatic regions, we may find that the answers lie not in the singularities themselves but in the deeper structures of spacetime and quantum mechanics that they reveal. Singularities challenge us to think beyond the familiar rules of physics and embrace the unknown. They remind us that our understanding of the universe is far from complete, and that the most profound mysteries may still lie ahead. Singularities may be the gateways to a new era of scientific discovery, one that will reshape our understanding of space, time, and the very nature of reality. And as we venture into these uncharted realms, we can only wonder what other cosmic secrets await us, hidden within the depths of the universe's most elusive phenomena. As we continue to delve deeper into the fascinating realm of singularities, we must also consider the very nature of the forces that dominate their existence. Singularities challenge everything we thought we knew about the interplay between space, time, and gravity. When matter is crushed into an infinitely small point, everything we understand about the mechanics of the universe breaks down. To some, this represents the ultimate puzzle, an enigma that not only questions our theories but also makes us reconsider the very nature of existence itself. To truly appreciate singularities, we need to revisit the history of our understanding of gravity. For centuries, scientists believed that gravity was merely a force that caused objects to fall towards the Earth, a straightforward concept. Isaac Newton's law of gravitation described this as a force of attraction that increased with mass and decreased with distance. However, the simplicity of Newton's law belied the complexities that would emerge in the centuries to come. In the early 20th century, Albert Einstein revolutionized our understanding with his theory of general relativity. He described gravity not as a force, but as the curvature of spacetime caused by mass and energy. According to general relativity, massive objects like stars and planets warp the fabric of spacetime around them, causing objects to follow curved paths in their gravitational field. This was a breakthrough, as it explained phenomena such as the bending of light around stars and the way planets orbit the sun. It also introduced the concept of black holes, regions of space where gravity is so intense that nothing, not even light, can escape. At the center of a black hole lies the singularity, a point where, according to general relativity, spacetime curvature becomes infinite. In such a region, all known laws of physics cease to function as we understand them. The equations that describe the behavior of matter and energy break down completely. But this poses a major problem. Physics cannot describe what happens at a singularity, leaving us with a void in our knowledge. This conundrum raises an even more fundamental question: what does it mean for the laws of physics to break down? We tend to think of the laws of physics as immutable, rules that govern the universe in a predictable and consistent way. But singularities challenge that assumption, suggesting that there are limits to our understanding, limits that even the most elegant theories cannot explain. This invites speculation about the very nature of the laws of the universe. Are they absolute and eternal, or do they evolve and change as we push further into the unknown? To gain insight into this, we turn to the realms of quantum mechanics. Quantum mechanics, which governs the behavior of particles at the smallest scales, operates on principles vastly different from the smooth, continuous picture of spacetime offered by general relativity. At the quantum level, particles exist in multiple states at once, and probabilities, rather than certainties, govern their behavior. But when quantum mechanics meets general relativity, it leads to contradictions. General relativity predicts singularities, while quantum mechanics says that such states should never exist in the first place. This tension between the two theories has led physicists to search for a unified theory, a theory of quantum gravity, that could seamlessly combine the principles of both. String theory, one of the most promising candidates for this theory of quantum gravity, proposes that the fundamental building blocks of the universe are not point-like particles but tiny, vibrating strings. These strings vibrate in different patterns, and their different vibrational states give rise to the particles we observe. String theory also suggests the existence of additional dimensions, beyond the familiar three of space and one of time, that could help reconcile the differences between quantum mechanics and general relativity. In string theory, the singularity might not be a point of infinite density at all. Instead, it might be a region where the fabric of spacetime itself is vibrating at extreme frequencies. In this scenario, singularities are not absolute breakdowns of the laws of physics, but rather places where our understanding of the universe is incomplete. String theory provides a glimpse into a reality where the smooth curves of spacetime give way to more fundamental, granular structures. Another possible approach to understanding singularities comes from loop quantum gravity, LQG. Unlike string theory, which requires extra dimensions and complex mathematical frameworks, LQG focuses on quantizing spacetime itself. It proposes that spacetime is composed of discrete, indivisible loops that form a kind of cosmic network. In this view, singularities are not infinite points, but rather areas where the loops of spacetime become highly curved and interact in complex ways. The loops are quantized, meaning they are composed of the smallest possible units of space, and as a result, singularities might be avoided altogether. One of the most compelling aspects of LQG is that it provides a potential resolution to the paradox of infinite density. According to this theory, as a star collapses to form a black hole, the very structure of spacetime begins to undergo quantum modifications. Instead of collapsing into an infinitely dense singularity, the star would reach a point where the loops of spacetime prevent further compression. The result would be a bounce, where the collapsing matter re-expands in a new form. This is known as the Big Bounce hypothesis, and it could provide a new perspective on the birth of the universe itself, suggesting that the Big Bang may have been the result of a previous universe collapsing in on itself, and then bouncing back into existence. This concept of a cosmic bounce has intriguing implications not only for our understanding of black holes but also for the nature of time and space. If the universe undergoes cycles of contraction and expansion, with each cycle being initiated by a bounce, it raises the question of whether time itself is cyclical. Could the universe be part of an eternal series of births and deaths, stretching infinitely into the past and future? Such a view of time challenges our conventional understanding of the universe as a one-time event, giving rise to profound philosophical questions about existence and the ultimate fate of the cosmos. Another critical aspect of singularities that has sparked both curiosity and concern is their relationship to the concept of causality, the principle that cause precedes effect. In classical physics, the idea of causality is fundamental. Events unfold in a predictable and orderly fashion. However, at the heart of a singularity, the laws of causality appear to break down. If spacetime becomes infinitely curved and distorted, the usual distinctions between cause and effect may no longer apply. This has led some to propose that singularities could be linked to phenomena like time travel or the creation of wormholes. Wormholes, which are theoretical shortcuts through spacetime, could potentially allow for faster-than-light travel or even connections between different regions of the universe. In some theories, a wormhole might be connected to a singularity, creating a bridge between distant parts of the cosmos. But the existence of such a structure is purely speculative, and the concept raises numerous questions about causality and the nature of time itself. Could wormholes allow us to travel backward in time, potentially altering the course of history? Or would they create paradoxes, where cause and effect become entangled in impossible ways? As we push the boundaries of our understanding of singularities, we find ourselves standing on the edge of a great unknown. The deeper we go, the more we encounter questions that seem to defy answers. Are singularities truly places of infinite density and destruction, or are they simply regions where our current understanding of physics breaks down? Could they be gateways to new realms of existence, offering glimpses of higher dimensional spaces or alternate universes? And perhaps most tantalizing of all, could singularities hold the key to unlocking the deepest mysteries of the cosmos, giving us a glimpse into the nature of reality itself? The study of singularities is far from over. As we continue to explore their nature and implications, we may find that the answers we seek are even stranger and more profound than we could ever have imagined. Singularities are not just points of curiosity, they are windows into the deepest questions of existence, and their mysteries will continue to captivate the minds of scientists, philosophers, and dreamers for generations to come. As we continue this journey into the heart of singularities, it's crucial to expand on the broader implications these mysterious phenomena have on our understanding of the universe. The ideas we've explored so far, such as the breakdown of laws of physics, the potential for quantum gravity theories, and the fascinating yet perplexing concepts of wormholes and time travel, all point toward one central conclusion: singularities hold the answers to some of the universe's most profound and challenging mysteries. These answers, however, are not easy to obtain, and they require us to look beyond the conventional models of physics. When considering singularities, one cannot overlook the fascinating paradox they present. The basic premise of a singularity is the collapse of matter into a point where space and time lose all meaning, where the fabric of spacetime is stretched to such extremes that it no longer behaves as we expect. And yet, despite being a theoretical concept, singularities have physical counterparts in the form of black holes. Observations of the universe, particularly the study of gravitational waves and the Event Horizon Telescope, have provided us with glimpses of the effects of these enigmatic structures. But even with all the advanced technology and scientific knowledge at our disposal, we are still far from fully understanding the behavior of singularities. In order to understand singularities more deeply, we must revisit the black holes in which they reside. The event horizon, the boundary surrounding a black hole, marks the point beyond which nothing, not even light, can escape. Once something crosses this threshold, it is inexorably pulled toward the singularity at the center. The nature of this journey, and the fate of the matter that crosses the event horizon, is one of the most profound mysteries in astrophysics. We have theoretical models that suggest that matter is crushed and compressed as it falls toward the singularity, but the specifics of this process are still shrouded in uncertainty. An important aspect to explore is the information paradox, a concept that arises in the context of black holes. In classical physics, information is thought to be a conserved quantity, meaning that it cannot be destroyed. However, when matter falls into a black hole, it seems as if all the information about that matter is lost. According to the principles of general relativity, the information about the matter that falls into a black hole is destroyed, but this violates one of the fundamental tenets of quantum mechanics, which insists that information must be preserved. This paradox has prompted the development of new theories, such as the holographic principle, which suggests that the information about a black hole's interior may not be lost but rather encoded on its event horizon in a way that we do not yet fully understand. Another intriguing question that arises when thinking about singularities is the role they play in the grand scale of the universe. Singularities are not just local phenomena confined to the interiors of black holes. They could hold the keys to understanding the large-scale structure of the cosmos itself. If, as some theorists suggest, singularities can lead to the formation of new universes or even act as conduits between different regions of spacetime, they might represent something much more profound than we currently realize. The possibility that black holes could be gateways to other parts of the universe, or even to entirely new universes, suggests that our universe might not be the only one in existence. This concept of multiverses has gained increasing attention in recent years, with many theoretical physicists suggesting that our universe may be just one of many, each governed by its own laws of physics. The idea that singularities could be the birthplace of other universes is a tantalizing prospect. In this scenario, when a black hole reaches its end stage, instead of simply collapsing into nothingness, it could give birth to a new universe. The singularity at the heart of a black hole could be a kind of cosmic seed, giving rise to a fresh universe with different physical constants and properties. This could mean that every black hole is, in essence, a portal to a new, separate reality, a theory that challenges our very understanding of space and time. The idea of singularities as the birthplace of new universes, however, is not without its problems. First, we must address the question of how the laws of physics would operate in these new universes. If the singularity is truly a point where space-time breaks down, how can it be the origin of a new universe governed by its own laws of physics? The answer may lie in the concept of cosmic inflation, a period of rapid expansion that occurred just after the Big Bang. Inflationary models suggest that the universe underwent an exponential expansion, smoothing out any irregularities and creating the large-scale structure we observe today. If singularities are indeed the birthplaces of new universes, then they may be linked to inflationary processes on a cosmic scale, generating new regions of spacetime where different physical laws take hold. This brings us to the heart of the unresolved mysteries that surround singularities, their role in the larger cosmic structure. Are they merely local oddities, or do they represent something far more fundamental? Could they be the keys to unlocking the true nature of the universe itself? The answers to these questions lie in the very fabric of spacetime, and to uncover them, we must continue to explore the most extreme conditions in the universe. One area of study that has garnered attention in recent years is the concept of the Fuzzball, a theory that arises from string theory. The Fuzzball model suggests that black holes are not actually singularities at all, but rather complex conglomerations of strings and branes, the fundamental building blocks of the universe in string theory. According to this model, the information that falls into a black hole is not lost but rather encoded in the complex web of strings and branes that make up the fuzzball. This idea challenges the conventional view of black holes as simple, smooth objects with a singularity at their center. Instead, it proposes that black holes are much more intricate and dynamic, composed of an intricate network of strings and energy fields. The fuzzball theory also raises important questions about the nature of gravity and spacetime itself. If black holes are not singularities, then what are they? And how does this new understanding of black holes affect our understanding of spacetime on the largest scales? The fuzzball model is still in its infancy, and much work remains to be done to determine whether it can provide a satisfactory resolution to the questions surrounding singularities. However, it is one of the many exciting avenues of research that are being pursued as we try to understand the true nature of these mysterious objects. As we delve deeper into the study of singularities, we are reminded that the universe is full of surprises. The deeper we look, the more we realize that our current understanding of physics is far from complete. Singularity research is not just a scientific pursuit, it is a quest to understand the very foundations of reality itself. Singularities challenge us to rethink the boundaries of space and time, to question the very nature of existence, and to consider the possibility of realities beyond our own. While we may never fully understand singularities in our lifetime, each discovery brings us one step closer to uncovering the secrets of the universe. As our understanding of the cosmos continues to evolve, singularities will remain a central focus of our efforts to probe the deepest mysteries of space, time, and gravity. With each new breakthrough, we edge closer to the ultimate understanding of the universe, and perhaps even the keys to unlocking the deepest mysteries of existence. As we press on, it becomes evident that singularities hold more than just the potential to reshape our understanding of physics. They represent a crossroads where all of our current theories and assumptions about the universe break down. If we look beyond the theoretical models and into the observable universe, singularities challenge us in ways that we are only beginning to comprehend. A major breakthrough in the study of singularities came in 2015, with the detection of gravitational waves by the LIGO Observatory. These waves, ripples in spacetime caused by the collision of two massive objects, are thought to be the result of black holes merging. The event was a landmark achievement in astrophysics, confirming many of Einstein's predictions regarding the nature of spacetime. However, it also posed new questions about the behavior of singularities. The collision of black holes produces gravitational waves, but once the black holes merge, what happens to the singularities at their centers? Do they remain separate, or do they merge into a single, even more mysterious entity? The nature of these post-collision singularities remains a point of intense debate. The more we study gravitational waves, the more we understand that singularities are not just a theoretical curiosity. They are, in many ways, active players in the cosmic drama. The ripples in spacetime caused by black hole mergers offer a glimpse into the innermost workings of these cosmic structures. They show us that even in the midst of a cataclysmic event like a black hole merger, the singularities themselves are still profoundly mysterious. As the gravitational waves travel across the universe, they carry with them information about the very nature of spacetime, allowing us to probe deeper into the heart of black holes than ever before. One of the key questions in this line of inquiry concerns the no-hair theorem. According to this theorem, once a black hole has reached equilibrium, it is characterized only by three properties: mass, charge, and angular momentum. This means that, in a sense, all black holes are fundamentally the same. Regardless of what falls into a black hole, its characteristics are reduced to these three properties. However, this theory has been challenged by recent research, which suggests that there may be additional factors that influence the behavior of black holes, factors that are not accounted for by the no-hair theorem. Some physicists have speculated that black holes may possess more complex internal structures, potentially related to quantum information or even unknown forms of matter. This line of thought leads to a more profound question: could singularities, in some sense, contain more information about the universe than we currently understand? The search for answers to this question is ongoing, and one of the most promising directions of research involves the study of quantum mechanics. In particular, quantum gravity, a field that seeks to reconcile the principles of quantum mechanics with those of general relativity, holds the potential to unlock the secrets of singularities. If we are to fully understand what happens inside a black hole, we need a theory that can bridge the gap between the very small, quantum particles, and the very large, cosmic objects like black holes and galaxies. This is where the search for a theory of quantum gravity becomes so crucial. One of the leading candidates for this theory is string theory. String theory posits that the fundamental particles of the universe are not point-like objects, but rather tiny, vibrating strings of energy. These strings can take on different forms, depending on their vibration frequencies, and they interact with one another in complex ways. According to string theory, the forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are all manifestations of the same underlying structure. This theory has the potential to offer a unified description of the forces of the universe, but it also has profound implications for our understanding of singularities. In the context of black holes, string theory suggests that the singularity at the center of a black hole may not be a point of infinite density, as traditionally thought, but rather a more complex structure made up of many strings and branes. This could mean that the gravitational collapse that leads to the formation of a black hole does not result in the destruction of information, as traditional theories suggest, but rather in the reorganization of information into a different form. The theory of black holes as Fuzzballs, mentioned earlier, is one potential interpretation of this idea, suggesting that singularities may be made up of an intricate web of strings and branes that store information in ways we do not yet fully understand. This idea challenges our traditional notion of a singularity as a point of infinite density and infinite curvature. If black holes are indeed fuzzballs, then the information about the matter that falls into them may not be lost at all, but rather encoded in the complex network of strings and energy fields that make up the fuzzball. This could provide a way to resolve the information paradox and reconcile the apparent conflict between quantum mechanics and general relativity. However, much work remains to be done to test these ideas and determine whether they hold true. While string theory offers one possible avenue for understanding singularities, other approaches, such as loop quantum gravity, are also being explored. Loop quantum gravity is a theory that attempts to quantize spacetime itself, treating it as a discrete structure rather than a continuous one. In this framework, the singularity at the center of a black hole would not be a point of infinite curvature, but rather a quantum structure that behaves according to the principles of quantum mechanics. This theory, like string theory, is still in its infancy, but it offers another promising way to approach the problem of singularities. At the heart of all of these theories is the desire to understand the true nature of spacetime. Is spacetime smooth and continuous, as suggested by general relativity, or is it discrete and quantized, as suggested by quantum theories? Are singularities real, or are they simply a product of the breakdown of our current theories? These are questions that we may not be able to answer in our lifetime, but they represent some of the most profound challenges in modern physics. As we continue to explore these questions, one thing is clear: singularities are not just theoretical oddities. They are essential to our understanding of the universe. They challenge our most fundamental assumptions about space, time, and gravity, and they point toward new, unexplored realms of science. Whether we ultimately discover that black holes contain fuzzballs, or that quantum gravity reveals a new way of looking at singularities, these cosmic enigmas will continue to drive our exploration of the universe for years to come. What we do know for certain is that singularities, with their immense gravitational pull and their profound effects on the fabric of spacetime, will continue to be a focal point for future research. They represent the ultimate frontier of our understanding, where the known laws of physics break down and new, mysterious forces come into play. As we seek to unravel the true nature of these cosmic phenomena, we may discover not only new aspects of the universe, but also new dimensions of reality itself. And in doing so, we will continue our quest for the answers to the greatest mysteries of the cosmos. As we continue this journey into the depths of spacetime and singularities, it's important to remember that our understanding of these cosmic phenomena is constantly evolving. Every observation, every new piece of data, and every theory that is put forth brings us closer to understanding what happens at the heart of a black hole. However, there are still many questions left unanswered, and the deeper we dive, the more we realize just how little we truly know. One of the key challenges in studying singularities is the fact that they are hidden behind event horizons. This means that we cannot observe the interior of a black hole directly. The event horizon is the boundary beyond which not even light can escape, making it impossible to gain any information about what is happening inside. As a result, we are left with only indirect evidence to guide our theories. This indirect evidence comes primarily from the effects that black holes have on their surroundings. For example, we can observe the behavior of matter and radiation as they approach a black hole. We can study the way light is bent and distorted by the intense gravitational field of a black hole, an effect known as gravitational lensing. We can also measure the way that stars and other objects move in the vicinity of black holes, using this information to infer the mass and size of the black hole itself. In recent years, the Event Horizon Telescope, EHT, has provided us with a groundbreaking new tool for studying black holes. In 2019, the EHT collaboration released the first ever image of a black hole's event horizon, located in the galaxy M87. This image, though blurry, marked a major milestone in our understanding of black holes. It provided us with direct evidence that black holes do, in fact, exist and that they are as mysterious and enigmatic as theorists have long believed. But even with this incredible achievement, the true nature of the singularity at the heart of the black hole remains elusive. The image captured by the EHT shows the shadow of the black hole, surrounded by a glowing ring of hot gas and plasma. This ring is created by the intense gravitational field of the black hole, which bends and distorts the light emitted by the surrounding material. The shadow itself is a direct consequence of the event horizon, the point beyond which nothing can escape. But the singularity, the point of infinite density and curvature, lies hidden within that shadow, unreachable by our instruments. The fact that we are able to capture images of black holes, even if they are not yet perfectly clear, is a testament to the incredible advances in technology and observational techniques. But it also highlights the fundamental challenge we face in studying singularities. We can observe their effects, but we cannot see them directly. This raises the question, will we ever be able to study the interior of a black hole? One possible way to study singularities in more detail is through the study of Hawking radiation. In the 1970s, physicist Stephen Hawking proposed that black holes are not entirely black, but rather emit a faint form of radiation known as Hawking radiation. This radiation is thought to be produced by quantum effects near the event horizon, where particles and antiparticles spontaneously form and annihilate. According to Hawking's theory, one of these particles may fall into the black hole, while the other escapes, leading to a gradual loss of mass and energy by the black hole. Hawking radiation, if it exists, could provide us with a unique way to study black holes from the outside. By measuring the radiation emitted by a black hole, we could potentially learn more about its properties, including the nature of the singularity at its core. However, detecting Hawking radiation is incredibly difficult. The radiation is extremely weak and would be nearly impossible to measure for most black holes, especially those that are far away. Nevertheless, the theory remains an important part of the conversation surrounding black holes and singularities, and any future discoveries in this area could significantly advance our understanding. Another avenue of research that could help us study singularities more directly is the study of quantum entanglement. Quantum entanglement is a phenomenon in which two particles become linked in such a way that the state of one particle is immediately correlated with the state of the other, regardless of the distance between them. This concept is central to quantum mechanics and has been experimentally verified in many different contexts. In recent years, physicists have begun to explore the relationship between black holes and quantum entanglement. Some researchers believe that quantum entanglement could play a role in resolving the information paradox, which arises when matter falls into a black hole. According to the information paradox, any information about the matter that enters a black hole is lost forever, violating the principles of quantum mechanics. However, recent work has suggested that quantum entanglement might provide a way for information to be encoded in the black hole's event horizon, allowing it to be recovered in some form. This idea is still very much in the realm of theoretical research, but it raises intriguing possibilities. If quantum entanglement can provide a means of recovering information from a black hole, it could offer a new way to study the singularity at its core. By examining the entanglement between particles inside and outside the event horizon, we may be able to uncover more about the true nature of black holes and singularities. Ultimately, the study of singularities is a complex and ongoing challenge that requires us to rethink many of the fundamental assumptions we have about the universe. The laws of physics as we know them simply break down when we try to describe what happens inside a black hole. Our current theories, such as general relativity and quantum mechanics, do not provide a complete picture of the universe, and the search for a unified theory that can account for both is one of the most ambitious goals in modern physics. One of the key questions that continues to arise in this context is the nature of spacetime itself. Is spacetime a continuous fabric, as general relativity suggests, or is it a discrete structure, as some quantum theories propose? The discovery of singularities, points where spacetime appears to break down, has forced us to confront this question in ways we never expected. If spacetime is truly continuous, what does it mean for a point to have infinite curvature? And if spacetime is discrete, what happens to the structure of the universe at the smallest scales? These questions are not just academic, they have real implications for our understanding of the universe. If we can solve the mystery of singularities, we may unlock a deeper understanding of how the cosmos works on both the grandest and smallest scales. We may uncover new aspects of the universe that we never thought possible, and we may find answers to questions that have puzzled humanity for centuries. As we move forward in our quest to understand singularities and their role in the cosmos, it is important to remember that we are standing on the shoulders of giants. The work of physicists like Einstein, Hawking, and others has laid the groundwork for the study of these mysterious phenomena, and their contributions continue to shape our understanding of the universe. But the journey is far from over, and there are still many mysteries left to uncover. Whether we are studying the effects of black holes on the fabric of spacetime, investigating the role of quantum mechanics in the formation of singularities, or developing new theories to explain the behavior of the universe at its most extreme, the search for answers will continue. As technology advances and our understanding deepens, we may one day unlock the secrets of singularities and gain a true understanding of the forces that shape the cosmos. Singularities may not just be points of infinite density and curvature, they may be the keys to understanding the very nature of reality itself. The mysteries of spacetime are vast, and the answers we seek may be even more profound than we can imagine. As we continue to push the boundaries of science and explore the unknown, we may find that the most profound mysteries of the universe are not the ones that we can see, but the ones that lie hidden in the heart of black holes, waiting to be discovered. As we continue to delve deeper into the mysteries of spacetime and singularities, it's crucial to understand that the quest to unlock these cosmic secrets is one of the most ambitious and challenging scientific endeavors ever undertaken. Singularities, those enigmatic points where the laws of physics break down, represent a fundamental challenge to our current understanding of the universe. But perhaps the most profound aspect of studying them is not just unraveling their secrets, but understanding the broader implications for how we perceive the fabric of reality itself. In many ways, the concept of a singularity is almost paradoxical. It's a region where space and time become infinitely warped, where the very foundations of physics fail to offer coherent descriptions. The equations that work so beautifully in most situations break down in the presence of a singularity, and what remains is a mathematical and conceptual void. This presents an inherent contradiction because, as scientists, we are taught to believe that every phenomenon should be explainable within the framework of natural laws. At the heart of this paradox is the fact that our two most powerful theories, general relativity and quantum mechanics, provide conflicting descriptions of the universe at the extremes. While general relativity describes the curvature of spacetime and the effects of gravity on massive objects like stars and black holes, quantum mechanics governs the behavior of particles at the smallest scales. Each theory has been incredibly successful in its own domain. However, when we try to apply them to singularities, the contradictions become apparent. In a singularity, gravity becomes so intense that the predictions of general relativity break down, and quantum mechanics, which governs the behavior of particles and forces at the smallest scales, doesn't have an adequate framework to explain the conditions near a singularity. In the face of these contradictions, scientists are searching for a theory of quantum gravity, one that can reconcile the two domains. This theory would offer a unified description of the universe that can explain both the vastness of cosmic structures and the minute behavior of particles. String theory, loop quantum gravity, and other approaches are being developed to address this need. Each offers a different perspective on how spacetime behaves at the most extreme scales, but no theory has yet emerged as the definitive explanation. What's more, these theories often involve concepts so far removed from our everyday experiences that they are difficult to even conceptualize. One of the main ideas in the quest for a unified theory is the notion that spacetime might not be a smooth, continuous entity, as described by general relativity, but rather a discrete or granular structure, as suggested by certain interpretations of quantum mechanics. According to this view, spacetime could be made up of tiny, indivisible units or quanta, similar to how matter is made up of atoms. If this is the case, then the infinite density of a singularity might not actually be infinite but could instead be a product of our current inability to perceive the granularity of spacetime. This concept challenges the very idea of what a singularity is. Perhaps, at the quantum level, the concept of infinite density doesn't even apply. Moreover, some physicists have proposed that singularities may not even exist in the way we imagine. Instead of being a point where the laws of physics break down, singularities might represent a transition between different types of spacetime, or they could be part of a much larger, more complex structure. For example, the idea of a fuzzball in string theory suggests that the core of a black hole might not be a singularity at all, but a highly entangled mass of strings that forms a complex, non-singular structure. This could mean that black holes, rather than harboring true singularities, could actually represent a kind of quantum transition between different states of spacetime. There is also the possibility that our understanding of singularities will evolve with advancements in observational technology. While we currently rely on indirect evidence to study black holes, future breakthroughs could allow us to observe these regions of spacetime in ways we can't yet imagine. For example, gravitational wave detectors like LIGO, Laser Interferometer Gravitational Wave Observatory, have already made groundbreaking discoveries by detecting ripples in spacetime caused by massive cosmic events like black hole mergers. As the sensitivity of these instruments increases, we may be able to probe deeper into the behavior of black holes and their singularities, potentially gaining new insights into their true nature. In addition to the direct observation of black holes, another avenue of research involves the study of cosmological models that incorporate singularities. One particularly fascinating example is the idea of the Big Bounce. This concept proposes that the universe may have gone through cycles of contraction and expansion, with each cycle ending in a singularity. Instead of the universe being created in a singularity at the Big Bang, the singularity could represent the end of a previous cycle. This model could offer a way to avoid the idea of a true beginning to the universe, instead suggesting that time and space are part of an eternal process of rebirth. Such ideas could ultimately change our understanding of both the nature of singularities and the origins of the universe itself. Even though these theories are still speculative, they open up fascinating possibilities for what could be discovered in the future. Each new hypothesis builds upon previous knowledge and gives us a glimpse into the extraordinary complexity of the universe. By combining observations with cutting-edge theoretical frameworks, we may one day uncover a complete picture of the universe's most mysterious phenomena. But while physicists and cosmologists wrestle with the theoretical aspects of singularities, it's essential to recognize how much we have already learned. The study of singularities has pushed the boundaries of human knowledge, leading to profound advancements in our understanding of spacetime, gravity, and the very nature of the cosmos. It has spurred the development of new mathematical techniques, advanced computational models, and revolutionary observational methods. Even if the mystery of the singularity is not solved in our lifetimes, the journey toward understanding it has already reshaped the field of physics and given us new tools for exploring the universe. As we push further into the depths of spacetime, we must also confront some of the broader philosophical and existential questions raised by the existence of singularities. What does it mean for our understanding of the universe that there are places where the laws of physics seem to break down? Does this suggest that there are limits to our understanding of the cosmos, or does it point to the possibility of deeper, more fundamental laws that we have yet to discover? The presence of singularities challenges us to rethink not only our scientific models but also our broader philosophical assumptions about the nature of reality. If space and time are not what they seem, if there are regions of the universe where the fabric of the cosmos is fundamentally altered, what does that say about our place in the grand scheme of things? Perhaps the very concept of a singularity, the idea of a point where the known laws of physics cease to apply, forces us to confront the idea that there are limits to what we can know. We may never be able to fully comprehend what happens inside a black hole, or what the true nature of spacetime is, but this doesn't diminish the importance of the search. The pursuit of knowledge, even in the face of the unknown, is what drives science forward and continually reshapes our understanding of the universe. As we continue to explore the nature of black holes, singularities, and the very fabric of spacetime, one thing is certain: the mysteries of the cosmos are far from being unraveled. Each discovery, each new piece of the puzzle, brings us closer to answering some of the most fundamental questions about the nature of existence. And though we may not have all the answers now, the search itself is a testament to humanity's unrelenting curiosity and desire to explore the unknown. As we continue our exploration of spacetime singularities, the inherent mysteries that lie within black holes become ever more tantalizing. Every new piece of evidence, every new theory, only deepens the enigma. But, as daunting as it may seem, this puzzle is one that might eventually help us unravel some of the deepest questions about the universe itself. Black holes and singularities are not merely curiosities in space. They offer a glimpse into the core of reality, challenging our notions of time, space, and the very laws that govern everything we know. In many ways, black holes serve as a natural laboratory for understanding the extreme conditions of the universe. At the event horizon, the boundary beyond which nothing, not even light, can escape, the effects of gravity are so intense that time itself seems to stretch. The closer we get to the singularity at the center of a black hole, the more bizarre the physics become. If we could somehow survive the passage through the event horizon and approach the singularity, the world we know would become unrecognizable. One of the most fascinating aspects of singularities is their connection to the concept of time. According to general relativity, time and space are intertwined in a single four-dimensional fabric known as spacetime. This fabric is curved by mass and energy, and gravity is simply the effect of that curvature. Near a black hole, this curvature becomes so extreme that time slows down relative to an observer far away. In theory, time at the event horizon could grind to a halt from the perspective of an outside observer. But from the perspective of someone falling into the black hole, time would continue to pass normally, until they reach the singularity itself. At the singularity, however, the effects of gravity are so strong that the fabric of spacetime itself becomes infinitely warped. This leads to what is known as the spacetime singularity, a point where density becomes infinite and the laws of physics as we understand them completely break down. In essence, the singularity represents a boundary of knowledge, a point beyond which we cannot predict what happens using current theories. It's a place where the very fabric of space and time ceases to behave in a way that is consistent with anything we can observe or experience. So, what does this mean for our understanding of the universe? The idea of a singularity suggests that there are regions of space where the universe behaves in ways that are completely foreign to us, where our most fundamental ideas about space, time, and reality itself are thrown into question. This is where the true mystery of the singularity lies. It's not just a place of extreme physical conditions, it's a place that challenges our most basic assumptions about the nature of existence. One intriguing possibility is that the singularity could represent the birthplace of a new universe. Some theories suggest that black holes might act as portals to other regions of spacetime, potentially even giving rise to new universes in a process known as cosmic inflation. This idea is part of a larger theory known as the multiverse, which posits that our universe is just one of many, each with its own set of physical laws and constants. According to this theory, when a black hole forms, it could create a baby universe, inside it, with its own distinct spacetime and physical laws. In this sense, singularities might not be the end of something, but rather the beginning of something entirely new, an entirely different realm of existence. Another fascinating possibility is that the singularity might be linked to the very beginning of our own universe. The Big Bang Theory suggests that the universe began as an infinitely dense point, often referred to as a singularity, and then expanded rapidly in an event known as cosmic inflation. This primordial singularity may have contained all the energy and matter that would eventually give rise to the universe we observe today. If black hole singularities share any similarity to the primordial singularity that marked the beginning of our universe, then the study of black holes and their singularities could provide insights into the very origins of everything that exists. However, as compelling as these ideas are, they remain speculative. The nature of singularities, and the role they play in the broader cosmos, is still a deeply unresolved question in physics. Our inability to directly observe or probe the interior of a black hole makes it incredibly difficult to gain concrete answers. But that doesn't mean scientists are standing still in their efforts to understand singularities. They continue to develop new theories and technologies to test the limits of our knowledge. One such theory is the idea of quantum gravity, which attempts to reconcile the seemingly incompatible worlds of quantum mechanics and general relativity. As mentioned earlier, these two pillars of modern physics have been extraordinarily successful in their respective domains but clash when applied to the extreme environments near singularities. Quantum gravity seeks to unify these two theories into a single framework that can describe both the large-scale structure of spacetime and the tiny particles that make up the fabric of the universe. By doing so, quantum gravity might provide a more complete description of what happens at the heart of black holes, possibly resolving the contradictions that arise when we attempt to apply both general relativity and quantum mechanics to singularities. One of the most exciting developments in the search for a theory of quantum gravity is the study of string theory. String theory posits that the fundamental building blocks of the universe are not particles but tiny, vibrating strings. These strings exist in higher dimensional space and can give rise to the various particles and forces that make up our universe. String theory has the potential to provide a unified description of all the fundamental forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces. Some versions of string theory suggest that black holes and singularities could be explained as the result of the interactions of these strings, offering a new perspective on the nature of spacetime and gravity. Loop quantum gravity is another promising approach to understanding singularities. This theory suggests that spacetime itself is quantized, meaning that it is made up of discrete units, or loops, rather than being a smooth continuum. According to this theory, the singularity at the center of a black hole might not represent a point of infinite density, but rather a transition to a different type of spacetime. In this view, the collapse of matter inside a black hole may eventually lead to the formation of a new, more stable structure, potentially avoiding the infinite density and the breakdown of physical laws that occur in traditional singularity models. Although loop quantum gravity remains an incomplete theory, it provides an exciting alternative to the traditional view of singularities and may eventually offer a more complete understanding of what happens in the extreme environments of black holes. In addition to these theoretical advancements, the study of black holes and singularities is being fueled by cutting-edge observational technology. Gravitational wave astronomy, which has already revealed the mergers of black holes and neutron stars, has the potential to unlock new insights into the behavior of black holes and their singularities. By studying the ripples in spacetime caused by these events, scientists hope to gain a better understanding of the structure of black holes and the fundamental nature of gravity. The upcoming generation of telescopes, such as the James Webb Space Telescope, is also poised to provide detailed observations of distant black holes and other cosmic phenomena, offering further clues about the nature of singularities and their role in the universe. As we look toward the future, the study of singularities promises to remain one of the most fascinating and mysterious areas of modern physics. Whether we are able to fully understand the nature of these cosmic anomalies or not, their study will continue to challenge our understanding of the universe and push the boundaries of what we know about the very fabric of reality itself. And perhaps, in the process, we will unlock some of the deepest mysteries of existence, helping to answer the ultimate questions about the origins of the universe, the nature of time, and the future of space itself. As we delve even further into the mysteries of space-time singularities, it's crucial to explore the broader implications of these cosmic enigmas. Singularities are not just isolated phenomena, they are deeply connected to the fundamental nature of the universe. Their study challenges everything from our understanding of gravity to the concept of time itself, and their mysteries may very well be the key to unlocking some of the deepest secrets about existence. At the heart of our exploration lies the understanding that black holes and their singularities define not only our current physics but also our intuition. The laws of physics as we know them break down in the presence of a singularity. In particular, general relativity, which governs the large-scale structure of the universe, and quantum mechanics, which describes the behavior of the smallest particles, both fail to provide a complete description of singularities. This is why scientists have long sought a theory of quantum gravity, one that can unify the two seemingly incompatible frameworks. But even if such a theory is developed, the singularity itself might still present a challenge that cannot be fully understood, at least not in the way we understand other cosmic phenomena. One fascinating aspect of singularities is their potential to reveal hidden dimensions of space and time. In many advanced theories of physics, such as string theory, it's proposed that the universe contains more than the familiar three spatial dimensions and one time dimension. Instead, there could be additional dimensions, beyond our perception, that govern the behavior of particles and forces at the most fundamental levels. Some researchers suggest that black holes, and especially their singularities, might provide a window into these extra dimensions. If this is true, then black holes could act as portals to a deeper layer of reality, where the known laws of physics no longer apply in their traditional forms. The concept of a singularity as a window to higher dimensions is still speculative, but it's one of the more intriguing ideas that arise when we attempt to reconcile general relativity with quantum mechanics. These extra dimensions could provide the necessary framework to explain phenomena like the behavior of black holes, the creation of new universes, or even the fundamental constants of nature. If we could access these dimensions, it might provide answers to some of the most profound questions in physics, including the nature of dark matter and dark energy, two of the biggest mysteries in contemporary science. Yet, despite the many theories and ideas surrounding singularities, there is still one overwhelming truth: we cannot yet probe these cosmic anomalies directly. Black holes, by their very nature, are hidden from our view. Their event horizons trap everything, including light, making them invisible to our telescopes. The best we can do is study the effects that black holes have on their surroundings. For example, the gravitational pull of a black hole can warp the space around it, distorting light and causing what is known as gravitational lensing. By observing this phenomenon, astronomers can infer the presence of black holes and even estimate their mass and size. But getting any closer to the singularity itself, whether in terms of direct observation or theoretical understanding, is an entirely different challenge. That's where gravitational waves come in. These ripples in spacetime, first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, have opened up a new way of studying black holes. Gravitational waves are produced by extremely violent events, such as the collision and merger of two black holes. By studying the waves generated by these events, scientists can learn more about the behavior of black holes and, indirectly, gain insights into the properties of singularities. This emerging field of gravitational wave astronomy could offer a new perspective on black holes and their singularities, perhaps even revealing phenomena that are invisible to traditional telescopes. One of the most intriguing implications of studying gravitational waves is that they might allow us to probe the behavior of spacetime itself. When two black holes merge, they create a violent disturbance in the fabric of spacetime, sending ripples through the universe that travel at the speed of light. By carefully analyzing these ripples, scientists can learn about the size, shape, and nature of the black holes involved in the merger, as well as gain indirect information about their singularities. This could provide vital clues about the extreme physics at play inside black holes, and potentially lead to new insights into the nature of the singularity itself. Furthermore, as technology improves and gravitational wave detectors become more sensitive, it's likely that we will be able to detect even more subtle events, such as the collision of neutron stars or the merging of supermassive black holes, that will shed more light on the behavior of spacetime near singularities. Each new detection brings us one step closer to understanding the true nature of black holes and their role in the universe. The more we learn about these cosmic objects, the closer we get to uncovering the secrets of singularities and what they tell us about the fabric of reality. In the near future, we may also have the ability to observe black holes in ways that were once thought impossible. The Event Horizon Telescope, a global network of radio telescopes, made history in 2019 when it captured the first ever image of a black hole's event horizon, the shadow cast by the black hole as light is bent around its immense gravitational field. This remarkable achievement marks a significant step in our ability to observe black holes directly. While the image captured by the Event Horizon Telescope doesn't provide a detailed view of the singularity itself, it does give us a new way of studying the outer regions of black holes and the behaviors that occur near the event horizon. As imaging technology advances, it's possible that we may one day be able to observe the interior structure of black holes, including their singularities. This would represent a monumental breakthrough in our understanding of these cosmic objects, and could provide us with the data needed to test our theories of quantum gravity. However, we must also acknowledge the limits of our technological capabilities. Even with the most advanced instruments, the sheer complexity and extreme nature of black holes may prevent us from fully understanding what happens inside them. While these efforts may seem daunting, they are an important part of the broader quest to understand the universe. The study of singularities is not just about black holes. It's about pushing the boundaries of what we know and challenging the very fabric of reality itself. Each discovery brings us closer to understanding the true nature of spacetime, and each breakthrough opens new doors to deeper mysteries. And perhaps, in the end, the singularity will remain an elusive mystery, one that we can only approach but never fully comprehend. Some scientists argue that the nature of singularities might forever be beyond our reach, given the limitations of our current understanding of physics. Yet, this does not diminish the importance of studying them. Even if we can never fully unlock their secrets, the search for answers to the mysteries of black holes and singularities has already led to profound advancements in our understanding of the universe. It has pushed us to question everything we thought we knew about space, time, and the fundamental laws that govern the cosmos. Ultimately, the study of space-time singularities is a journey that reflects our desire to explore the unknown and to understand the universe in all its complexity. And though the path may be long and fraught with challenges, each step forward brings us closer to unraveling the deepest mysteries of existence. Whether or not we ever uncover the true nature of singularities, the quest for knowledge will continue, driving us to explore new frontiers and redefine our understanding of the cosmos. The pursuit of understanding singularities, however elusive, reveals a profound and fundamental truth: the universe is far more complex and strange than we could ever have imagined. And while the singularities at the centers of black holes are the most extreme manifestations of spacetime's bending, there are other phenomena that, in their own way, push the limits of our understanding even further. These events and objects challenge the very essence of what we know about the laws of physics, questioning whether the boundaries we've established in the realms of space, time, and gravity are as rigid as they seem. As we continue to study black holes and their singularities, we are confronted with the reality that there are still many fundamental questions left unanswered. For example, what happens to the information that falls into a black hole? This question is at the heart of the so-called black hole information paradox, a problem that has sparked intense debate among physicists for decades. According to classical physics, once something crosses the event horizon of a black hole, it is lost forever, including all the information about its state. But quantum mechanics, the theory that governs the behavior of subatomic particles, insists that information cannot be destroyed, only transformed. The apparent contradiction between these two principles lies at the heart of the paradox. Some theories suggest that the information may be stored in a way that we do not yet understand, perhaps on the event horizon itself, in a phenomenon known as holography. According to the holographic principle, the information about a three-dimensional object or system can be encoded on a two-dimensional surface. This idea has its roots in string theory, where it is suggested that the entire universe might be a projection from lower-dimensional space. If this is true, the information that falls into a black hole might not be lost, but rather encoded in a manner that is beyond our current comprehension. The nature of this encoding and whether it's accessible to us remains one of the biggest open questions in theoretical physics. Another area where the singularity comes into play is the concept of time itself. In the vicinity of a singularity, time behaves in ways that are completely alien to our everyday experience. According to Einstein's general theory of relativity, the intense gravitational field of a black hole warps spacetime so severely that time appears to slow down for an observer as they approach the event horizon. This effect, known as time dilation, has been experimentally verified on a smaller scale, such as with satellites orbiting the Earth, where time moves slightly faster than on the planet's surface due to weaker gravity. But near a black hole, this time dilation becomes extreme. For an observer falling into a black hole, time would appear to slow down as they approach the event horizon, and from the outside, it would seem as though they never quite reach it. This strange behavior of time raises even deeper questions about the nature of reality. If time behaves so differently near a singularity, it suggests that our conventional understanding of the flow of time may not hold in the extreme environments near black holes. Some physicists have proposed that singularities might represent a breakdown of time itself, where the usual rules no longer apply. In such a scenario, time could become a completely different phenomenon altogether, one that we cannot fully understand with our current models. Furthermore, The issue of time and singularities is also tied to the concept of the Big Bang, the event that is thought to have marked the birth of our universe. In fact, the singularity at the center of a black hole and the singularity at the moment of the Big Bang are believed to share many similarities. Both represent points in spacetime where the curvature of spacetime becomes infinite, and where the known laws of physics fail. Understanding one may, in theory, provide insights into the other. If we could solve the mysteries of black hole singularities, we might gain a better understanding of the birth of the universe itself. However, there is a fundamental difference between the two types of singularities. The singularity at the Big Bang is thought to have occurred in the past, at the very beginning of time, whereas the singularities in black holes exist in the present, within the fabric of the universe. This distinction leads to another intriguing question: is there a way to connect these two concepts? Could the study of black hole singularities help us unlock the mysteries of the early universe? Or could they hold the key to understanding what happens after the universe's eventual end? These are questions that challenge not just our scientific knowledge, but also our philosophical understanding of the cosmos. In more recent years, some researchers have speculated that the singularities we observe in black holes might not even be the end points of spacetime, but rather gateways to other universes. This idea stems from the concept of a multiverse, in which our universe is just one of many existing simultaneously in a higher dimensional space. In this scenario, black holes could act as bridges between these universes, with the singularity at the center of a black hole serving as a conduit to another, parallel universe. While this idea is still highly speculative and not widely accepted by mainstream physics, it raises fascinating possibilities about the interconnectedness of all the universes and the true nature of reality itself. Theoretical work on the multiverse and the nature of black hole singularities is still in its infancy, and many of these ideas remain unproven. However, even the possibility that singularities might be more than just dead ends in spacetime is enough to spark the imagination of scientists and laypeople alike. The mysteries surrounding singularities are not just about understanding a small corner of the universe. They are about seeking a deeper truth about the nature of existence, time, and space. It's worth noting that the study of black holes and singularities also has far-reaching implications beyond physics and cosmology. The pursuit of understanding the nature of spacetime may one day offer practical applications in technology and science. For instance, some scientists speculate that the insights gained from studying black holes might one day lead to advancements in energy generation, space travel, or even information processing. If we can fully understand the complex behavior of singularities, we might discover ways to harness the incredible forces at play in these regions, creating technologies that are beyond our wildest imaginations. As we continue to explore the cosmic mysteries of singularities, we should also keep in mind the extraordinary progress humanity has made in understanding the universe. Just a few hundred years ago, our knowledge of the cosmos was limited to what could be seen with the naked eye. Today, we have telescopes and detectors that allow us to peer into the farthest reaches of space, and we are on the verge of discovering even more groundbreaking phenomena. Our understanding of black holes and singularities has come a long way, but the road ahead is still long and uncertain. Every new discovery about these mysterious objects brings us closer to unlocking the most profound questions about the universe. And perhaps, as we learn more about singularities, we may come to realize that they are not just a scientific mystery to solve but a reminder of how much there is still to explore and discover. They remind us that no matter how much we think we know about the universe, there is always more to learn. The singularity, in its infinite complexity, will continue to elude our understanding. But in the search to understand it, we will uncover new layers of knowledge that may one day change the way we view the universe, and perhaps even ourselves. As we continue to peel back the layers of spacetime and singularities, it's essential to explore how these cosmic enigmas not only challenge our understanding of physics, but also redefine the very boundaries of knowledge. The pursuit of answers surrounding black holes and their singularities is akin to venturing into uncharted territories. The mysteries are so profound and complex that they stretch the limits of what we, as human beings, can comprehend. But the very fact that we can formulate questions about them, even without all the answers, speaks to the depth of our curiosity and the potential of human discovery. One of the most mind-bending aspects of singularities is the concept of infinite density. In classical general relativity, when you enter a black hole, you approach the singularity at its center where the curvature of spacetime becomes infinite. But what does infinite density really mean? According to Einstein's equations, as matter falls into a black hole, it gets squeezed into an ever smaller space, and the density increases without bound. Essentially, all the mass of the black hole is thought to occupy a point of zero volume, where gravitational forces are so intense that they overwhelm everything: time, space, and even the laws of physics themselves. This point of infinite density might be the most extreme version of what we refer to as breakdown of physics. In a practical sense, this means that the equations we use to describe space and time stop working altogether. There's no way, using current mathematical models, to describe what happens at this point, no method of bridging the gap between general relativity and quantum mechanics. This is one of the key reasons why singularities are such a thorn in the side of physicists. To complicate matters further, there's a possibility that the actual structure of the singularity is not a point at all. Quantum mechanics, which governs the behavior of the smallest particles in the universe, suggests that at the quantum level, space and time may be fuzzy, rather than smooth. This has led to speculation that singularities, rather than being an infinitely dense point, could be regions where spacetime behaves in entirely new, unknown ways. This would require a new theory that combines quantum mechanics and general relativity, what scientists refer to as quantum gravity. There are several competing theories that attempt to explain what happens within the singularity. One of these is loop quantum gravity, which suggests that spacetime itself has a discrete structure, like a network of loops. According to this theory, rather than collapsing into an infinitely dense point, the fabric of spacetime would reach a quantum bounce, where it would resist further collapse. If this theory holds, it could offer a way to avoid singularities altogether, suggesting that the very nature of spacetime has limits and cannot collapse indefinitely. Another approach comes from string theory, which posits that all particles are not point-like, as we have traditionally thought, but are instead tiny, vibrating strings. In this framework, the intense gravity inside black holes could cause these strings to vibrate in ways that would prevent the formation of a singularity. String theory also predicts the existence of additional dimensions, beyond the familiar 3 dimensions of space and 1 of time, potentially allowing new forms of spacetime that might bypass the formation of singularities as we understand them. These ideas are still in their infancy, but they point to a future where our understanding of singularities might evolve in ways that seem almost fantastical by today's standards. One of the most fascinating aspects of singularities is their connection to time itself. Near a black hole's event horizon, time is stretched and warped to the point where it behaves almost counterintuitively. The phenomenon of time dilation, a consequence of Einstein's theory of general relativity, is so extreme near a singularity that time for an observer falling into the black hole would appear to stop altogether from the perspective of someone far away. In a sense, the very flow of time breaks down, which raises the question, what happens to an object that falls into a black hole? From the perspective of the falling object, time would continue normally. But from the perspective of an outside observer, as the object approaches the event horizon, it appears to slow down more and more, eventually freezing in place. This is a manifestation of what physicists call space-time curvature. The closer an object gets to the singularity, the stronger the gravitational field becomes, warping the fabric of spacetime around it. The implications of this extreme warping of spacetime go beyond our understanding of time and space. They challenge the very idea of what it means for something to exist or to move through time. Is time the same everywhere? Does it flow differently depending on the gravitational influence of nearby objects? These are questions that could radically change how we think about not only space and time but also the concept of reality itself. Moreover, as strange as it may sound, there's a possibility that the intense gravitational forces near a singularity could affect the fundamental constants of nature. For example, the speed of light, which is considered a universal constant, could behave differently in the intense gravitational fields near a singularity. Some physicists have even suggested that black holes might allow us to probe fundamental questions about the nature of the constants that govern our universe. But there's a deeper question at play here. If singularities represent such a breakdown of our understanding, what does that say about the very laws of physics themselves? Are the laws of physics truly universal, or do they break down under extreme conditions, like those at the center of a black hole? The quest to understand singularities is not just a scientific challenge, it's a philosophical one, raising profound questions about the nature of reality, the limits of human knowledge, and the very fabric of the universe itself. As we continue to study black holes and singularities, we're faced with the humbling realization that the universe may be far more mysterious than we've yet begun to grasp. We are only beginning to scratch the surface of the complex interplay between gravity, quantum mechanics, and the fabric of spacetime. The further we delve into the heart of these cosmic enigmas, the more we realize how much we still don't understand. Yet, this is what makes the study of singularities and black holes so compelling. They represent the ultimate frontier of science, where the known laws of physics break down and new, mind-bending possibilities arise. In the quest to unlock the secrets of these enigmatic objects, we're not just probing the deepest corners of the universe. We're probing the very nature of existence itself. In the future, new observational techniques and theoretical breakthroughs may provide us with answers, or at least lead us closer to the truth. As we continue to study the strange and mysterious phenomena that black holes present, we might discover new ways of thinking about spacetime, gravity, and the fundamental laws of the universe. But perhaps the most intriguing part of this journey is that, with each answer we uncover, new questions will undoubtedly emerge, keeping the mysteries of singularities as one of the most fascinating and profound puzzles in all of science. For now, we remain in the dark about many of the deepest questions of the cosmos. But it is in this darkness that we find the spark of curiosity, the drive to explore the unknown. The mysteries of singularities will undoubtedly continue to captivate scientists, philosophers, and thinkers for generations to come, as we seek to understand what lies at the very heart of the universe itself. The quest to understand singularities and black holes doesn't just extend to theoretical physics. It also pushes the boundaries of observational technology. For decades, our understanding of these cosmic objects was limited to equations and models. But in recent years, we've seen an explosion of new discoveries, many of which have allowed us to test the limits of our knowledge in ways once thought impossible. One of the most significant breakthroughs in this regard came in 2019, when the Event Horizon Telescope, EHT, released the first-ever image of a black hole's event horizon. This historic image showed the shadow of the supermassive black hole at the center of the galaxy M87, revealing a glowing ring of gas and light bent by the extreme gravity of the black hole. This image confirmed many predictions of general relativity, but it also opened up new avenues for exploration, including the study of the behavior of light and matter near the event horizon. By observing the way light behaves around black holes, scientists hope to gain more insights into the nature of the singularity itself. But even with this major advancement, observing the core of a black hole remains incredibly challenging. The intense gravitational forces near a black hole distort space and time so much that they warp the path of light itself. This makes it incredibly difficult to get a clear view of what's happening at the very center. In fact, no direct observation of the singularity has been made, and we may never be able to observe it in the way we observe other cosmic phenomena. What we can study, however, is the surrounding environment, the accretion disk, the jets of matter being ejected, and the light bending around the event horizon. These observations give us crucial clues about the nature of the singularity and its influence on the fabric of spacetime. Looking ahead, new technologies and advancements in telescope design could one day allow us to peer even closer into the mysteries of black holes. For instance, next-generation space observatories like the James Webb Space Telescope, JWST, may help us study the environments of black holes in unprecedented detail. By observing infrared radiation from the surrounding matter, JWST could reveal more about how black holes grow and interact with their surroundings. Similarly, the Laser Interferometer Space Antenna, LISA, a space-based gravitational wave observatory, is designed to detect ripples in spacetime caused by massive black hole mergers. These ripples, or gravitational waves, carry information about the behavior of matter under extreme gravitational conditions, which could shed light on the true nature of singularities. However, even with these advanced tools, there will always be questions that remain tantalizingly out of reach. This is the beauty and the frustration of studying singularities. They represent both the edge of our understanding and the gateway to new frontiers. We may never fully comprehend the singularity itself, but the journey toward understanding it is likely to yield new insights into the laws of physics, the nature of reality, and the structure of the universe. The implications of studying singularities extend far beyond the confines of black holes. In fact, these objects may hold the key to unlocking some of the most profound mysteries of the universe. For example, the behavior of matter and energy near a singularity could help us understand the nature of dark matter and dark energy, two of the most elusive and mysterious components of the cosmos. Some researchers speculate that the gravitational effects seen near black holes could reveal clues about the fundamental forces that govern the universe, potentially helping to unify the four known forces of nature: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Moreover, understanding singularities could offer insights into the origins of the universe itself. The idea that the universe began as a singularity, a point of infinite density and temperature, has been central to cosmological models of the Big Bang. If we can understand how singularities form and behave in black holes, we may be able to learn more about the conditions that existed at the very beginning of the universe. This could help answer questions about why the universe began in the first place, what happened during the earliest moments of the Big Bang, and whether the laws of physics were the same at that time as they are today. As we explore these questions, we must confront a crucial issue: the limits of human knowledge. Singularities, by their very nature, may forever be beyond our complete understanding. They challenge the very foundation of physics, where the laws we use to describe the universe break down. In many ways, singularities remind us of the limits of our perception and the finite nature of human understanding. The more we learn about the cosmos, the more we realize how much we still don't know. There are still many fundamental questions left to answer. Is the universe infinite, or does it have an edge? What lies beyond the event horizon? Can we ever truly understand what happens inside a black hole? These are questions that we may not have answers to for centuries, if ever. But the pursuit of answers is part of what makes the study of black holes and singularities so compelling. Every discovery we make brings us closer to a more complete picture of the universe, even if the ultimate truth remains elusive. For now, we continue to push the boundaries of science, hoping that the answers to these mysteries will eventually emerge from the cosmic fog. The study of singularities is not just a quest to understand a particular phenomenon. It is a journey into the heart of reality itself. Singularities challenge our concepts of space, time, and matter, and in doing so, they force us to confront the very limits of human understanding. They are a reminder that the universe is far stranger and more complex than we can possibly imagine, and that the true nature of reality may be beyond our current ability to comprehend. As we continue to explore the mysteries of singularities, we are reminded of how much we still have to learn. Each new discovery takes us one step closer to understanding the forces that shape our universe, but it also reveals just how much more there is to uncover. In the end, it is this infinite quest for knowledge, this insatiable curiosity, that drives us to continue asking the big questions, even when the answers seem impossibly distant. And perhaps, in the pursuit of these cosmic mysteries, we will eventually uncover truths that will redefine our understanding of the universe and our place within it. The journey of uncovering the secrets of singularities is not just about understanding these enigmatic points of infinite density within black holes, but it also stretches into the deepest fabric of our universe itself. It forces us to challenge the fundamental assumptions we hold about reality, pushing the boundaries of what we thought was possible in the realm of physics. These phenomena, so deeply entwined with the mysterious workings of the cosmos, may contain answers not just to the nature of black holes but to some of the most profound questions of existence itself. One key concept in our exploration of singularities is the idea of quantum gravity, which seeks to reconcile the two major pillars of modern physics, general relativity and quantum mechanics. General relativity, Einstein's theory, brilliantly describes the behavior of large-scale cosmic objects like stars, galaxies, and black holes. On the other hand, quantum mechanics governs the strange, microscopic world of subatomic particles. The problem arises when trying to combine these two theories in situations where both are relevant, such as near the singularity at the center of a black hole. At a singularity, the gravitational forces are so immense that they cause space and time to warp and bend in ways unimaginable in our everyday experience. According to general relativity, at this point, space and time become infinitely curved, which leads to a breakdown of the laws of physics as we know them. Meanwhile, quantum mechanics governs the behavior of particles at the smallest scales, where randomness and uncertainty dominate. The problem is that these two theories are fundamentally different, and when trying to apply both to singularities, they appear incompatible. This is the heart of the issue that scientists face today, the quest for a theory of quantum gravity. Quantum gravity aims to unify these two theories into a single framework that can describe the behavior of spacetime at all scales, from the subatomic to the cosmic. One of the leading candidates for such a theory is string theory, which posits that the fundamental building blocks of the universe are not point-like particles, as traditionally thought, but rather tiny, vibrating strings. These strings could potentially be the key to resolving the mysteries of singularities, providing a quantum mechanical description of the gravitational forces at play. In string theory, the singularity at the center of a black hole might no longer represent a point of infinite density, but rather a region where the fundamental strings themselves behave in a way that evades the classical description of spacetime. Rather than reaching an infinite density, the strings might be stretched and compressed in such a way that they prevent the formation of a true singularity. This is still highly speculative, as string theory itself is far from proven, and the mathematical models required to test it are incredibly complex. But it presents an exciting possibility for resolving the tension between quantum mechanics and general relativity. Another approach to understanding singularities comes from loop quantum gravity, a competing theory to string theory. Loop quantum gravity suggests that spacetime itself is quantized, consisting of discrete chunks, or loops, at the smallest scales. According to this theory, instead of a smooth, continuous fabric of spacetime, the very nature of space and time is made up of tiny, indivisible loops. In this model, the extreme conditions near a black hole's singularity could result in a bounce, rather than a collapse to infinite density. Rather than matter being crushed into an infinitely small point, the laws of quantum gravity could prevent this collapse, leading to a new understanding of what happens inside a black hole. While these theories represent the forefront of modern physics, they still struggle with one fundamental issue: the lack of direct observational evidence. Singularities remain elusive, and the nature of the quantum realm is, by its very nature, difficult to observe. Our tools and techniques are simply not advanced enough to directly test these ideas in the extreme environments near black holes. This makes the pursuit of a theory of quantum gravity particularly challenging, as much of the work remains in the realm of mathematics and abstract theory. Despite these challenges, advances in technology continue to provide new ways to probe the mysteries of black holes and singularities. For example, gravitational wave astronomy, a field that exploded into prominence with the detection of the first gravitational waves in 2015, has opened up new opportunities for observing the behavior of black holes. Gravitational waves are ripples in the fabric of spacetime caused by the acceleration of massive objects, such as the collision of black holes. These waves carry information about the properties of the objects that created them, including their mass, spin, and the dynamics of the merger. By studying the waves produced by black hole mergers, scientists are able to learn more about the extreme physics near singularities, even without being able to observe the singularity itself. The recent discovery of gravitational waves has already provided incredible insights into the nature of black holes, including the confirmation of binary black hole systems and the observation of black hole mergers. These findings have opened up entirely new avenues of research, providing a way to test theories of gravity and explore the behavior of matter and energy in ways that were previously impossible. In the future, as gravitational wave detectors become more sensitive and sophisticated, we may be able to study the fine details of black hole interactions and potentially gain new insights into the very nature of singularities. Looking even further ahead, there may be breakthroughs in quantum computing that allow us to model and simulate the extreme conditions near a singularity with far more precision than ever before. Quantum computers could perform calculations that are currently beyond the reach of classical computers, potentially providing us with more accurate models of black holes and the nature of spacetime at the quantum level. These developments could accelerate our understanding of the universe and perhaps even reveal new phenomena that we have not yet imagined. One fascinating area of research that ties into the study of singularities is the idea of information paradoxes. This paradox, first proposed by Stephen Hawking, centers around the idea that information about matter falling into a black hole seems to be lost forever. In classical physics, this would violate a fundamental principle of quantum mechanics, the idea that information is never truly lost, only transformed. This paradox has led to heated debates and alternative theories about what happens to information inside a black hole. Some scientists propose that the information is not lost but rather stored in a form that we cannot yet detect, possibly on the event horizon itself in the form of holographic data. This idea, known as the holographic principle, suggests that the entire universe, or at least the information contained within it, could be encoded on a two-dimensional surface. The implications of this idea are profound, as they suggest that the three-dimensional world we experience could be a projection of data encoded in two dimensions. As we continue to probe the nature of singularities, it's clear that we are approaching a turning point in our understanding of the cosmos. Every new discovery brings us closer to unraveling the secrets of these mysterious objects. But with each answer, new questions emerge, and the mysteries of the universe become even more complex. Singularities, by their very nature, embody the limits of our knowledge, challenging us to rethink everything we know about space, time, and the fundamental forces of nature. As we venture deeper into the unknown, the pursuit of understanding black holes and singularities will continue to shape the future of physics. It is a journey that will not only reveal the true nature of the universe but also redefine our place within it. In the end, the study of these cosmic anomalies is not just about finding answers, but about exploring the very nature of reality itself. The road ahead in the quest for understanding singularities and black holes is an exciting one, filled with both challenges and immense possibilities. As our tools and theories evolve, we may soon begin to unlock even deeper layers of the universe's mysteries. Singularities are more than just regions of space where gravitational forces overwhelm everything. They are the ultimate puzzles that push the boundaries of everything we know, testing our understanding of the very fabric of spacetime. One of the most intriguing aspects of singularities is their relationship with the concept of time itself. In general relativity, time is intertwined with space to form the four-dimensional continuum known as spacetime. But near the singularity, this concept is stretched and warped in ways that are difficult to grasp. Space and time are no longer the familiar dimensions we experience in our everyday lives, and this could lead to paradoxical situations. For instance, time as we know it may effectively stop at the singularity, and this raises profound questions about causality and the nature of the past, present, and future. The idea of time breaking down at a singularity has fascinated physicists for decades. Time dilation, the slowing down of time in strong gravitational fields, is already a well-established concept in the theory of general relativity. But at a singularity, this effect becomes extreme. To an outside observer, it appears that time at the event horizon of a black hole would stand still, and as you approach the singularity, the distortion in time becomes increasingly severe. However, for an object falling into a black hole, the passage of time would feel normal to them. This stark contrast highlights how warped our understanding of time becomes in the presence of a singularity. Even more mind-boggling is the potential idea that time may be cyclical, looping back on itself within the singularity. This brings us to the theory of white holes, a hypothetical inverse of black holes. While black holes swallow matter and light, white holes theoretically eject them. Some physicists speculate that these white holes could be connected to the singularities in black holes, offering a fascinating possibility. Could singularities serve as portals to other regions of spacetime, or even other universes? The concept of wormholes, tunnels through spacetime, grows from these ideas, suggesting that the singularity might be a gateway, not just a point of infinite density. Such theories are, of course, highly speculative, but they offer tantalizing possibilities. If we could somehow access the information inside a black hole or gain a better understanding of how time behaves in these extreme environments, we might discover entirely new laws of physics, ones that could redefine our perception of the universe itself. The idea that singularities could lead to new dimensions or even new realms of existence challenges everything we know about reality. And in doing so, it opens up entire new fields of thought, from the nature of the cosmos to the potential for parallel universes. As we explore these concepts further, we begin to realize that the study of singularities isn't merely an academic exercise. It may very well hold the key to unlocking some of the most profound secrets of the universe. Perhaps the singularity is not just a failure of our current theories, but an opportunity, a signpost pointing us toward a deeper understanding of how the universe truly works. What if the key to understanding the entire cosmos lies hidden within these regions of infinite gravity? Despite the intriguing theories, the practical hurdles of testing them are enormous. Our current technology is not capable of observing the interior of a black hole directly. We can only study the effects of black holes on their surroundings, such as how they warp light, bend spacetime, or influence the motion of nearby stars. The Event Horizon Telescope, which famously captured the first image of a black hole's event horizon in 2019, marks a monumental step in this direction. But still, the singularity itself remains far beyond our reach. However, with advances in computational physics, scientists are developing increasingly sophisticated simulations to model the extreme conditions near singularities. These simulations use the power of supercomputers to create virtual models of spacetime under intense gravitational forces. By tweaking these models and comparing them to real-world data from telescopes and gravitational wave detectors, researchers can explore what might be happening inside a black hole. It's an indirect method of observation, but one that could ultimately lead to a better understanding of these enigmatic regions. Moreover, future observatories and space missions might provide us with even more tools to study black holes. The proposed LISA, Laser Interferometer Space Antenna, mission, for example, aims to detect gravitational waves in space, offering a new way to study the ripples caused by black holes and other massive objects. By observing these waves in even greater detail, we might be able to gather more information about the internal dynamics of black holes, including their singularities. Space-based gravitational wave detectors could provide insights that are impossible to obtain from Earth-based instruments, pushing our understanding of spacetime to new heights. Another avenue of exploration is the search for quantum signatures, subtle effects that could provide clues about how quantum mechanics operates near singularities. Some scientists believe that quantum effects like quantum foam, a type of quantum fluctuation at the smallest scales, may manifest in the extreme conditions near black hole singularities. These quantum signatures might be detectable through future experiments, providing valuable information about how matter behaves at the most fundamental levels. As we delve deeper into these investigations, we might also uncover new principles of physics that could have far-reaching implications. The study of singularities could challenge the very foundation of our understanding of space, time, and matter. It could provide insights into the origin of the universe itself, and the nature of the laws that govern it. Concepts like time loops, alternate dimensions, and the potential for life or information to escape from a black hole might seem like science fiction, but as we push the boundaries of physics, these ideas become increasingly plausible. The implications of these discoveries would not only deepen our understanding of the cosmos but could revolutionize technology in ways we can't yet imagine. The potential applications of advanced quantum technologies, inspired by the study of black holes and singularities, might lead to breakthroughs in fields ranging from computing to energy production. Understanding how information behaves in extreme conditions could lead to more efficient data storage methods, for example, or even new ways to harness the energy of black holes themselves. Singularities stand as one of the final frontiers of our knowledge, and as we continue to explore them, we approach the very edge of human understanding. The mysteries surrounding them are not just academic, they are profound questions that have the power to reshape our view of the universe and our place within it. Each new breakthrough brings us closer to answers, but also reveals new mysteries that challenge everything we thought we knew. The study of singularities is not just about understanding black holes, it is about unraveling the deepest truths of existence itself. Singularities are not just a scientific curiosity, they represent the greatest puzzle of our time. As we explore the heart of darkness, we might uncover the keys to understanding the fabric of reality itself. And in doing so, we may discover that the universe is far stranger, far more complex, and far more beautiful than we could have ever imagined. The journey through singularities and their implications for physics is only just beginning. As we dig deeper into the concept of spacetime singularities, we find ourselves confronting fundamental questions about the very structure of reality. These questions aren't just theoretical exercises, but rather windows into the deepest workings of the universe. By understanding singularities, we can explore the limits of our knowledge and the potential for new scientific revolutions. As previously discussed, singularities are regions where our current understanding of physics breaks down. The laws of general relativity, which describe how mass and energy warp spacetime, fail to provide a complete description inside a singularity. As an object crosses the event horizon of a black hole, it reaches a point where the gravitational forces become infinite. The core of the singularity is where all the mass is concentrated, a place where density and gravity are so intense that they push the known laws of physics to their breaking point. It is here that we run into the fundamental conflict between general relativity and quantum mechanics, the two pillars of modern physics that have yet to be reconciled into a unified theory. One of the most compelling aspects of black hole singularities is their potential connection to quantum mechanics, which governs the behavior of particles at the smallest scales. Quantum mechanics and general relativity are two incredibly successful theories, but they operate under different sets of rules. Quantum mechanics describes the behavior of particles at the atomic and subatomic levels, while general relativity is the theory of gravitation that governs the behavior of massive objects in the universe. When these two worlds collide at the center of a black hole, it creates a paradox. To reconcile these two theories, physicists have been searching for a quantum theory of gravity. The hope is that such a theory could explain the behavior of gravity at the scale of individual particles and provide a more complete description of singularities. Several approaches to this problem have been proposed, with one of the most promising being string theory. String theory suggests that the fundamental particles of the universe are not point-like objects, but rather tiny, vibrating strings. These strings could potentially offer a way to bridge the gap between quantum mechanics and general relativity by providing a unified framework that incorporates both theories. Another approach is loop quantum gravity, which attempts to quantize the fabric of spacetime itself. According to loop quantum gravity, spacetime is made up of discrete units, or quantum loops, which means that the smooth continuum of spacetime described by general relativity may only be an approximation at large scales. In the context of black holes, loop quantum gravity suggests that the singularity at the center of a black hole may not be a point of infinite density, but rather a region where spacetime itself undergoes quantum fluctuations. This could prevent the formation of a true singularity, offering a possible resolution to the paradox between general relativity and quantum mechanics. Both string theory and loop quantum gravity are still highly speculative and face significant challenges. They have not yet been experimentally verified, and their predictions are difficult to test with current technology. However, they represent some of the most promising paths toward a deeper understanding of singularities and the fundamental nature of spacetime. If these theories are correct, they could revolutionize our understanding of the universe, providing insights into everything from the behavior of black holes to the origins of the cosmos itself. But the implications of singularities go beyond just theoretical physics. They also challenge our understanding of space and time on a philosophical level. The idea that time could break down at the singularity, or that our perception of causality may not hold in these extreme environments, forces us to reconsider what we know about the nature of reality. If time and space behave so differently near a singularity, it raises the question, what happens to the flow of time in these regions? Is there a way to measure time inside a black hole? Can events inside a black hole have any influence on the outside universe? Some physicists have proposed the idea that black holes could potentially be linked to alternate universes. If we could somehow escape the singularity, we might find ourselves in a parallel universe where the laws of physics are different from our own. This idea is supported by the theory of multiverses, which suggests that our universe is just one of many, each with its own set of physical laws. In this scenario, the singularity at the center of a black hole could serve as a bridge between different universes, allowing information, and perhaps even matter, to travel between them. This concept of a multiverse challenges our traditional understanding of the universe as a self-contained entity. It opens up the possibility that the observable universe we see around us is only a tiny fragment of a much larger, more complex reality. While the idea of alternate universes is still speculative, it is a fascinating area of study that has the potential to reshape our understanding of space, time, and the nature of existence itself. While much of this remains theoretical, recent discoveries are beginning to provide new insights that could bring us closer to understanding singularities and their role in the universe. Gravitational wave astronomy, for example, has opened up a whole new window into the study of black holes. By detecting the ripples in spacetime caused by the collision and merger of black holes, scientists are gaining valuable information about the behavior of these enigmatic objects. These observations may provide new clues about the interior structure of black holes and the nature of singularities. The detection of gravitational waves has already provided a wealth of information, but we are still in the early stages of this new field. As more advanced detectors come online, such as the Laser Interferometer Space Antenna, LISA, we may be able to gather even more precise data on black holes and singularities. These observations could allow us to test some of the most challenging hypotheses about black holes, such as the behavior of matter inside them, the structure of the event horizon, and the potential for quantum effects to emerge in extreme gravitational environments. The study of singularities and black holes is also helping to drive advances in computational science. The development of powerful supercomputers has enabled scientists to simulate the behavior of matter and light in the presence of extreme gravitational forces. These simulations allow researchers to model the dynamics of black holes and explore what might happen inside them. By comparing these simulations to real-world observations, scientists can refine their theories and gain new insights into the nature of singularities. In the future, these simulations may help us answer some of the most profound questions in physics. For example, can we predict the ultimate fate of matter inside a black hole? Can information really be lost inside a singularity, or is there a way to retrieve it? These questions have implications for everything from the fate of black hole mergers to the preservation of information in the universe. By understanding how singularities affect the flow of time and matter, we can learn more about the fundamental principles that govern the universe. Singularities, as strange and puzzling as they are, remain one of the most exciting areas of scientific inquiry. They challenge our understanding of space, time, and gravity, and they offer the potential for groundbreaking discoveries that could reshape our view of the cosmos. The search for answers continues, driven by the belief that within these enigmatic regions of space lies the key to unlocking the most profound secrets of the universe. As we look to the future, we can expect to see even more discoveries in the field of black holes and singularities. With each new breakthrough, we move one step closer to understanding the nature of spacetime, the limits of our knowledge, and the possibility of new realms of existence. The mysteries of singularities are far from solved, but the pursuit of these answers is one of the most exciting and transformative endeavors in modern science. The study of singularities is not just a quest to understand extreme conditions in the universe. It is a journey that pushes the boundaries of human knowledge and challenges our most basic assumptions about the nature of reality. With each new discovery, we are inching closer to a deeper understanding of the universe, and perhaps even the discovery of new dimensions of existence that we can hardly imagine. As we continue to explore the mysteries of singularities, it's important to understand that their implications extend beyond just the physical laws of the universe. They challenge the very fabric of reality as we know it. Singularities, especially those hidden within the heart of black holes, force us to rethink the concepts of space and time themselves. These are not merely theoretical anomalies. They are tangible phenomena that push our understanding to the limit. One key aspect of black hole singularities that has captivated physicists and cosmologists for decades is the idea of the information paradox. According to classical physics, any object that falls into a black hole is lost to the universe forever. Once it crosses the event horizon, it is pulled into the singularity, a point where space-time curvature becomes infinite. In this framework, information about the object, its particles, properties, and state, is lost to the universe. However, this presents a serious issue when we consider the principles of quantum mechanics. Quantum theory asserts that information cannot be destroyed. This is known as the no-deletion theorem, which states that no physical process can completely erase information. This fundamental conflict between general relativity and quantum mechanics has led to what is now called the black hole information paradox. In order to resolve this paradox, scientists have proposed a number of hypotheses. One of the most widely discussed is the idea of holographic principle. This principle, formulated by physicists such as Gerard T. Hooft and Leonard Susskind, suggests that all the information contained within a three-dimensional region of space, such as a black hole, could be encoded on the two-dimensional boundary of that region. In this context, the singularity inside a black hole may not represent the destruction of information, but instead could act as a kind of projection or hologram, where all the details of the infalling matter are encoded on the event horizon. This concept has led to groundbreaking theories about how black holes might actually preserve information. One possibility is that the information might be stored on the event horizon itself, in the form of quantum entanglement. Quantum entanglement is a phenomenon where particles become linked in such a way that the state of one particle instantaneously affects the state of another, no matter how far apart they are. This interconnectedness might allow information to be encoded on the event horizon of a black hole, preventing it from being lost inside the singularity. Another hypothesis is that the information could be released in the form of Hawking radiation. In 1974, physicist Stephen Hawking proposed that black holes are not completely black but instead emit small amounts of radiation, which could slowly cause them to lose mass and eventually evaporate. This radiation, now known as Hawking radiation, could potentially carry information about the matter that once fell into the black hole. If this is true, it would mean that black holes do not destroy information, but rather slowly leak it out over time. The resolution of the black hole information paradox remains one of the most significant challenges in modern theoretical physics. The answers to these questions may reveal profound new insights into the nature of space, time, and the fundamental laws that govern our universe. Understanding how information is preserved or lost within black holes could not only help solve this paradox but also shed light on other areas of physics, such as the nature of quantum gravity and the behavior of particles at extreme scales. As we consider the future of singularity research, it is clear that new observational techniques will be critical in deepening our understanding. The Event Horizon Telescope, EHT, which captured the first image of a black hole in 2019, marks a major milestone in the study of black holes. By observing the shadow of the event horizon, scientists were able to capture a visual representation of a black hole's immediate environment, providing direct evidence of its existence. This achievement opens the door for more detailed studies of black holes and singularities. But what if, beyond the observational breakthroughs, we are on the verge of discovering entirely new types of black holes, ones that challenge our current models? For example, physicists have speculated about the existence of naked singularities, which are singularities that are not hidden behind an event horizon. In this case, the singularity would be directly observable, providing an unprecedented view into the nature of extreme space-time curvature. However, the existence of naked singularities is highly controversial and remains unproven, as the cosmic censorship conjecture posits that such singularities cannot exist in nature, as the laws of physics would prevent them from being observed. Nevertheless, the mere possibility of naked singularities challenges our understanding of black holes and singularities. If such objects exist, they could provide critical insights into the behavior of spacetime in extreme conditions and help us better understand the limitations of general relativity. Even more radical ideas are being explored in theoretical physics. For example, the concept of a wormhole has long been associated with singularities. Wormholes are hypothetical passages through spacetime that could connect distant regions of the universe or even different universes entirely. These connections are believed to be linked to black holes, as the extreme gravitational forces inside black holes could, in theory, create bridges between different points in spacetime. If wormholes exist and can be traversed, they might offer a shortcut through the cosmos and allow for interstellar travel that defies our current understanding of space and time. While these ideas may seem like science fiction, they are grounded in mathematical models and are taken seriously by some physicists. If we can ever find a way to test these hypotheses or discover new phenomena related to singularities, it could open up entirely new realms of physics and lead to groundbreaking advances in our understanding of the universe. There's also the question of whether singularities might play a role in the larger structure of the cosmos. Some researchers have speculated that the formation of black holes and singularities could be linked to the creation of new universes. According to certain models of cosmology, the collapse of a massive star into a black hole could trigger a Big Bang in another region of space, potentially giving rise to a new universe with its own laws of physics. This idea is part of the broader concept of the multiverse, where multiple, possibly infinite, universes exist in parallel, each with its own set of physical laws. The formation of black holes and the emergence of singularities may be part of a process that produces new universes, adding yet another layer of mystery to the already complex nature of singularities. The nature of singularities is not just a theoretical puzzle, it has practical consequences for our understanding of the universe. If we can unlock the secrets of black holes and singularities, we may be able to develop new technologies that could revolutionize space exploration. For example, understanding the nature of black holes could help us find ways to harness their energy, or even use them as potential sources of power for deep space missions. As we learn more about the extreme environments around black holes, we may also gain insights into the behavior of matter and energy in other extreme situations, such as those found near neutron stars or in the early universe. Ultimately, the study of singularities offers us a chance to explore the limits of human knowledge. These enigmatic objects are not just puzzles to be solved, they are invitations to rethink everything we know about space, time, and the laws of physics. The pursuit of understanding singularities is a journey that may take us to the very edge of our comprehension of the universe. As we continue to explore these cosmic mysteries, we may find that the questions we ask about black holes and singularities are just the beginning of a much larger journey into the heart of the cosmos. As we continue to dive deeper into the realm of singularities and black holes, it becomes clear that these cosmic phenomena are not just limited to theoretical explorations, but could lead to real breakthroughs in our understanding of the universe. One of the most intriguing aspects of black holes is their ability to influence the fabric of spacetime itself. Einstein's theory of general relativity predicts that a black hole's immense gravitational pull warps spacetime to such an extreme degree that it essentially bends space and time around it. At the singularity, this distortion becomes infinitely sharp, creating a point where the laws of physics as we know them break down. This breakdown of physics is not just an academic curiosity, it poses real challenges to our understanding of the universe. For instance, the singularity inside a black hole is believed to be a point where gravity is so intense that it overcomes all other forces, including electromagnetism, the strong nuclear force, and the weak nuclear force. All matter that crosses the event horizon is compressed into this infinitely dense point, which raises an important question: what happens to the information about the matter that falls in? The answer to this question is not simple. According to the principles of quantum mechanics, the information that describes the state of a physical system cannot be lost. This is known as the quantum information problem, and it is at the heart of the black hole information paradox. If information is lost at the singularity, it would violate the rules of quantum mechanics. On the other hand, if information is preserved, we would have to radically rethink our understanding of gravity and spacetime. This tension between quantum mechanics and general relativity is one of the greatest unsolved problems in modern physics. Several theories have been proposed to resolve this paradox. One of the most compelling is the idea of black hole complementarity, which was introduced by physicists Leonard Susskind, Gerard T. Hooft, and others. According to this theory, information is not lost when it falls into a black hole. Instead, it is encoded on the event horizon, the boundary surrounding the black hole, and can be recovered by observing the radiation emitted from the black hole. However, this process of encoding and decoding information remains highly speculative and has yet to be confirmed by any direct evidence. Another possible resolution to the information paradox comes from the concept of firewalls. This idea, proposed by physicists Almhiri, Merov, and others, suggests that the event horizon of a black hole might not be a smooth boundary after all. Instead, it could be surrounded by a wall of fire that destroys any information that crosses the event horizon. This would effectively solve the information paradox by destroying the information in a way that is consistent with the laws of quantum mechanics. However, the firewall hypothesis is highly controversial, and many physicists still believe that information is somehow preserved. Another fascinating possibility involves the nature of time itself within a black hole. According to Einstein's theory of general relativity, time slows down dramatically as one approaches the event horizon. This effect, known as gravitational time dilation, suggests that from the perspective of an outside observer, time appears to come to a complete standstill at the event horizon. But for an object falling into the black hole, time would continue to pass normally. In fact, the object would eventually reach the singularity, where the gravitational forces are so extreme that they would likely be torn apart. This raises an important question: what happens to time beyond the event horizon? Some scientists speculate that the concept of time may break down entirely inside a black hole. In this view, the singularity might represent not just a point of infinite density, but also a boundary where time ceases to exist as we know it. In this scenario, the usual laws of cause and effect would no longer apply, and the concept of time itself would become irrelevant. This idea challenges our deepest intuitions about the nature of reality and suggests that our understanding of space-time is far more complex than we could have ever imagined. Despite these challenges, the study of singularities and black holes is not just about solving theoretical problems. It also has profound implications for how we understand the universe as a whole. The study of these extreme environments provides a unique opportunity to test the limits of our scientific theories and gain new insights into the fundamental nature of reality. For example, the discovery of gravitational waves, ripples in space-time caused by the acceleration of massive objects, has already opened up a new era in our understanding of the universe. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the first direct evidence of gravitational waves from the collision of two black holes. This discovery provided direct confirmation of one of the most important predictions of Einstein's theory of general relativity, and opened up a new way of studying the cosmos. Gravitational waves allow scientists to observe phenomena that were previously invisible, such as the merging of black holes and the behavior of matter in extreme gravitational fields. By studying these waves, scientists can gain new insights into the nature of black holes and singularities, as well as test the predictions of various theories of gravity. This observational breakthrough has the potential to revolutionize our understanding of the universe and answer fundamental questions about the nature of space, time, and gravity. In the future, we may be able to observe even more exotic phenomena, such as the behavior of matter near the singularity itself. As technology advances, we may develop new techniques for probing the interiors of black holes and singularities. Instruments such as the Event Horizon Telescope, EHT, which captured the first image of a black hole's event horizon in 2019, are pushing the boundaries of observational astronomy. By studying the electromagnetic radiation emitted from the area around black holes, scientists can learn more about the structure of these enigmatic objects and perhaps even uncover new physics that has never been observed before. As we explore the mysteries of black holes and singularities, we must also confront the possibility that these objects may not be the ultimate limit of our understanding. There may be even more extreme and exotic phenomena lurking in the universe, waiting to be discovered. For example, some scientists speculate that there may be objects known as fuzzballs that are distinct from black holes but still exhibit similar properties. These objects, which are predicted by certain versions of string theory, could provide a new framework for understanding singularities and the nature of spacetime. The study of singularities is still in its infancy, and there is much that we do not yet understand. However, as we continue to explore the nature of black holes and the extreme environments around them, we are bound to uncover new and surprising insights into the fundamental laws of the universe. The mysteries of spacetime and singularities are far from being solved, but each new discovery brings us one step closer to unlocking the deepest secrets of the cosmos. The study of singularities is a journey into the unknown, where the boundaries of our understanding are constantly being tested. From the breakdown of classical physics at the event horizon to the paradoxes that arise when quantum mechanics and general relativity collide, singularities challenge everything we thought we knew about the universe. Yet they also offer us an opportunity to expand our knowledge and explore the deepest questions about space, time, and the nature of reality itself. As we continue to probe the mysteries of black holes, we may one day uncover the ultimate truth about the universe's most enigmatic and powerful objects. As we continue to explore the enigmas surrounding black holes and spacetime singularities, one cannot help but wonder if these objects hold the key to unlocking some of the most profound mysteries in physics. One aspect of black holes that remains tantalizing is the fact that they challenge our very understanding of space and time. They serve as a crucible for testing the limits of our scientific models, where the forces at play far exceed anything we can directly experience here on Earth. The more we study black holes, the more we encounter paradoxes that force us to reconsider our assumptions about the fabric of the cosmos. One such paradox, known as the no-hair theorem, suggests that black holes are incredibly simple objects. According to this theorem, a black hole is completely described by just three properties: mass, charge, and spin. These three characteristics supposedly determine the black hole's appearance and behavior, making them seemingly featureless objects. However, this simplicity hides the true complexity of what might be happening within the black hole's event horizon. The no-hair theorem came under scrutiny in the context of the black hole information paradox, which we discussed earlier. The paradox arises from the tension between quantum mechanics and general relativity, two pillars of modern physics that, on their own, are extraordinarily successful at describing different aspects of the universe. However, when these two theories are applied to black holes, we find that they make conflicting predictions about how matter behaves inside a singularity. While general relativity predicts a complete breakdown of the laws of physics at the singularity, quantum mechanics insists that information about the state of the universe must be preserved. This brings us to the idea of quantum gravity, a theoretical framework that aims to reconcile these two seemingly incompatible theories. Quantum gravity seeks to describe the gravitational force in terms of quantum mechanics, potentially allowing us to understand black holes at a deeper level. The idea is that quantum effects should become important at very small scales, like those near the singularity, where both quantum mechanics and general relativity operate simultaneously. One of the leading approaches to quantum gravity is string theory, which posits that fundamental particles are not point-like objects but instead tiny, vibrating strings. According to string theory, the behavior of these strings gives rise to the forces of nature, including gravity. String theory suggests that black holes may not actually contain a singularity at all, but instead might have a more complex structure known as a fuzzball. In this picture, the singularity is replaced by a fuzzy state of matter, and the traditional picture of a black hole is fundamentally flawed. String theory and its related ideas, such as the multiverse theory, challenge our conventional understanding of space, time, and reality itself. The notion that the universe could consist of multiple, parallel universes, each with its own laws of physics, is both mind-boggling and profoundly philosophical. It raises the possibility that black holes might be gateways to other realms of existence, perhaps allowing information to travel between parallel universes or offering a means of escaping our own. However, these ideas remain speculative and highly controversial, with little empirical evidence to support them. Nevertheless, the theoretical work surrounding singularities, quantum gravity, and string theory is pushing the boundaries of human knowledge. The possibility that our universe could contain a hidden structure or layer of reality, one that we cannot perceive with our senses, has profound implications not only for our understanding of physics but also for our understanding of the very nature of existence. As we continue to probe the mysteries of black holes and singularities, we are also uncovering more about the universe's most fundamental properties. One of the most fascinating developments in recent years has been the growing realization that the fabric of spacetime itself may not be as smooth and continuous as we once thought. Instead, some researchers believe that spacetime may be quantized, meaning that it is composed of discrete units, much like how matter is made up of atoms. If spacetime is indeed quantized, then the very concept of a singularity may need to be rethought. Instead of a point of infinite density, the singularity could represent a region where the fabric of spacetime is extremely compressed, but not infinitely so. This might resolve some of the paradoxes associated with black holes and lead to a new understanding of how spacetime behaves in extreme environments. Recent discoveries related to quantum entanglement and the holographic principle also have the potential to shed light on the nature of black holes and their singularities. The holographic principle, in particular, suggests that the three-dimensional universe we experience may be a projection of information encoded on a two-dimensional surface, much like a hologram. This idea, which was first proposed by physicists Gerard T. Hooft and Leonard Susskind, is deeply connected to black holes and could offer a way of resolving some of the puzzles associated with them. According to the holographic principle, the information contained within a black hole may not be lost but rather encoded on its surface, or event horizon. This idea has been supported by studies of black hole thermodynamics, which suggests that the surface area of a black hole's event horizon is related to its entropy, the amount of information it contains. If this is true, then black holes might serve as a kind of information storage device, preserving the information about the matter that falls into them, even as that matter is no longer accessible from the outside. Moreover, the study of quantum entanglement, an essential feature of quantum mechanics, could help explain how information is preserved in black holes. Quantum entanglement describes a phenomenon where the properties of two particles become linked in such a way that the state of one particle immediately influences the state of the other, no matter how far apart they are. This strange property of quantum mechanics might play a crucial role in understanding how information is encoded and preserved inside black holes, even though it seems to defy our classical intuitions. While all of these ideas are still very much in the realm of theoretical physics, they represent some of the most exciting and innovative approaches to understanding black holes, singularities, and the structure of the universe itself. As technology advances and our observational capabilities improve, we may one day be able to test these ideas directly and uncover new truths about the fundamental nature of reality. In the meantime, the mysteries surrounding black holes and singularities remain some of the most fascinating and perplexing puzzles in science. Each new discovery about these cosmic objects brings us closer to understanding not only the extreme environments they create, but also the very fabric of the universe. Whether through advancements in quantum mechanics, general relativity, or the development of new observational techniques, the study of black holes is bound to continue to shape our understanding of the cosmos for years to come. As we peer into the darkness of black holes and singularities, we are reminded that our understanding of the universe is far from complete. The very nature of spacetime and gravity remains an open question, and as we continue to probe these enigmatic objects, we may one day discover a new, deeper layer of reality, one that could forever alter our understanding of the universe and our place within it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.